Okay, all right. So the YouTube is now up and running. It is live streaming the Zoom webinar, and the Zoom webinar is up. We have a number of attendees. Thank you, everybody, for joining me. Thank you to all the LSI grant winners for joining here today. We're really looking forward to hearing from each and every one of you about some of the things you guys are thinking about doing. My name, for those on the Zoom webinar and on the YouTube, my name is Sonny White. I'm the Director of Advanced Research and Development at Limitless Space Institute. LSI is a 501c3 nonprofit that started in 2019. And our mission is all about inspiration, education, and research, specifically as it traces to enabling human exploration of the outer solar system and beyond. And as part of that, we have this program we call LSI Grants and Fellowships. And this is a way for us to partner with academia and fund professors from all over the globe that have some interests that kind of trace to some of the same interests that we have. And so the purpose of LSI grants is to try and fund gritty and credible research, to try and make some measurable progress and on a number of fronts that we're very interested in from a mission perspective for LSI. If you would, I'm going to give a one-page overview of Limitless Space Institute. And then after that, I would actually like to share with everybody a video that we just commissioned that kind of gives an overview of LSI. So this will, I think, be the first time it'll be kind of broadcast in a public venue. So give me just a second here while I share my screen, share sound. All right, can everybody see my screen? You get a thumbs up?
Yes.
Okay, all right, very good. Okay, this is a quick thumbnail overview of Limitless Space Institute. Our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. The three pillars of Limitless Space Institute are inspire, educate, and research. And our long-term vision, our pinnacle objective, if you will, is to work to try and enable interstellar travel by the turn of the century. And LSI is a doing organization. We're trying to, basically put our money where our mouth is, if you will. And so we have a number of programs that are meant to try and put rubber on the road to try and make measurable progress like this. We have internal research that we do in our lab called EagleWorks. We've been working for DARPA Defense Science Office for a while on some stuff, continuing to work forward on some stuff that would probably be viewed as what's beyond quantum mechanics, what's beyond general relativity. And so we've been conducting that.
By the way, Sonny, this is Pete Warden. I didn't get an invite, so I'm on James' invite. He's had a travel disaster, so he's on airlines right now.
Oh, copy. All right. Hey, thank you, Pete. It's really good to see you join us. It's going to.
I'm only be able to stay on for a bit, but James is supposed to be here, but he had a travel disaster.
I'm so sorry to hear that. I hope he's okay.
Yeah, I didn't get an invite for this anywhere.
Yeah, I'll have to. We'll go make sure we fix that. So sorry about that.
No problem. All right, no problem. I'll be on for a while.
Okay, awesome. So in addition to the work that we do internally with EagleWorks, we fund work externally through the LSI grants, like I just talked about. And we do this in partnership with Texas A&M and Breakthrough Initiative. So Pete just joined. He is the head of the Breakthrough Initiatives. And so this is a biennial program that we conduct every 2 years. We did do a 2020 to 2022 cycle. And so this is the second biennial cycle from 2022 to 2024. And so we'll be hearing from all of you about your awesome ideas and plans. We are definitely interested in how this connects with education. We've got with the LSI grants, we have a good connection with universities, graduate students and such, but we also want to extend our efforts into the K through 12. So we have something we call our Limitless Educator Program that was stood up by Casey Hines, who just joined the team as our Director of Education. And so we have partnered with 20 educators in the K through 12 range from all over the globe to try and develop classroom materials and lesson plans that'll be freely available for folks to be able to use to teach about some of the things that map to our mission and our objectives. We have some other programs, scholarships, LSI lab boosters, internships. We've done a summer class with the Initiative for Interstellar Studies, and we still have an active university partnership with Texas A&M working on a portable nuclear reactor. And Landon Zinski, our friend over here, that's at the table with me. He's a nuclear program super wonk from NASA headquarters, and he's been helping with that as well. So we're really glad he's able to join us here today. And he'll actually be our keynote as we kick things off here in just a second. But this is a overview of the schedule. So for folks that are online with the webinar, after Landon Zinski gives his opening remarks on NASA nuclear initiatives, we will go into a series of TED Talks where our grant performers will be giving us an overview of what it is they intend to do as part of the award that we've given them. And there will be no questions during the individual presentations. We will have a 20-minute period of facilitated Q&A. So just trying to keep everything tight on the schedule. And then we'll have a 20-minute break in between in our case, in Texas, the morning session and the afternoon session. And for our folks that are much further over in Europe, your afternoon section and your evening section, I'm sorry, is trying to balance the different timescales. And then we'll have the 5 talks in the afternoon, again, followed with some facilitated Q&A. So we'll try and stay as close to this schedule as we can. I will do my best when the talks start to give each one of you like a 3-minute warning, just to let you know you're right at the 3 minutes, and try and keep it as close as you can to 20 minutes. So we can have a little bit of flexibility, but try and keep it at 20 minutes. I think the other value proposition of keeping it at 20 minutes is that it also gives you good practice at synopsizing your story in a brief but not superficial fashion. So and then with that, let me share my video here real quick, and then we'll get some opening comments from Len. Let's see. Yeah, I should have shared my sound. So when I press play, and I get a thumbs up from folks that you can hear the sound.
This generation has set their eyes on the moon and Mars. But even these relatively close destinations are at the very limits of today's human-rated systems. To go any farther requires traversing much greater distances and will require a significant leap in what's possible with power and propulsion in space. We believe these advancements will reap untold benefits for life on Earth, and so we have set our sights on achieving interstellar human space travel by the end of the century. Limitless Space Institute is dedicated to advancing human exploration beyond our solar system by inspiring the next generation through research and education to break the limits of what is possible.
I've been asked many times why I wanted to get involved and help start up LSI. And it's pretty straightforward. After nearly 4 decades of service to my country and NASA, I wanted to pay it forward. Our challenge is to set goals extremely high, to push and to lead positive change, to enhance working together and ultimately humanity's strive for peace and new technologies.
We are fostering integrity, courage, and imagination through 2 foundational efforts of research and education.
LSI is both conducting and sponsoring the very research necessary to enable human beings to go past Mars in our solar system and one day on to the stars. For this type of capability, we need to look to solutions such as nuclear electric propulsion, fusion propulsion, and even the frontiers of physics to potentially develop breakthrough propulsion concepts such as space warps or even wormholes.
To this end, LSI is partnering with universities and research organizations intent in fostering the incremental studies that can lead to measurable advances.
We know that the future workforce that's going to be working on these advanced power and propulsion systems are in classrooms across the country and around the world today. The Limitless Space Institute is inspiring the next generation through our Limitless Educator program. So who is our key player in this mission? Those are our educators. That's who we want to inspire, who then can go and inspire students in these classrooms.
When I was really thinking about it in terms of how vast the universe is, the word limitless came to my mind. But the idea that I had was more about giving back. LSI is a nonprofit and get to really inspire, educate, and do research and development for humans to go to stars, because I believe that the ultimate destination.
As large as the universe is, the farthest humans have traveled is 158 miles beyond our own moon. As much as has been developed in 60 years of space travel, the fastest humans have traveled is 24,791 miles an hour. With growing support from those who believe we can go farther, the possibilities are limitless.
All right, thank you for letting me share that with you guys. I'm going to hand the microphone over here to Landon Zinski. Let's see, I'm pulling up your charts here.
Great. Thank you, Sonny.
Sure thing. So this is Landon Zinski, a NASA nuclear super awesome human being. He's going to give us some amazing inputs on what NASA is doing. So I'll pull up the charts. And then you just tell me when to page down, I'll page down.
All right, so I'll just say a few words by introduction. My name is Landon Zinski. I'm from NASA headquarters. I am the Chief Technologist for the Planetary Science Division. And I'm honored to be able to talk to you all this morning about the work that NASA is sponsoring in nuclear power and propulsion. Certainly, it's an honor to address such an august group of researchers. You all are doing some amazing work that's really on the vanguard of power and propulsion that, as the video just demonstrated, is really going to push the boundaries beyond our solar system. What I'm going to be talking about with all of you this morning is really the foundational work that NASA is doing that's going to enable exploration in the near term to the moon and Mars, and perhaps beyond with robotic probes. But certainly what you all are doing is going to take what I'm talking about this morning to the next level. So it's really exciting to be talking to you all about that. If you take to the next slide, this is kind of a combined talk. The way NASA has things organized, I'm in the Planetary Science Division. I work on radioisotope power systems as their program executive. We also have Dr. Anthony Calamito in the Space Technology Mission Directorate, and I have some of his material as well to talk to you about. He's the one who's managing the work in the nuclear fission, both power and propulsion work that NASA is sponsoring. And so I'll be sharing both visions for both work for both Planetary Science Division and STMD this morning. Next slide. So why does NASA invest in nuclear power and propulsion? Well, first of all, we need to provide that reliable energy production that's essential for human and scientific exploration throughout the solar system, where solar power is really impractical, and also to provide that enhanced performance necessary to get both scientific probes and eventually humans beyond Earth orbit and beyond the moon. Nuclear power enables energy-dense systems that can operate continuously in areas where the sun's energy is not available, or where the distance traversed or the time for the mission is impractical for other energy solutions such as batteries. We are working and sharing with a shared interest in these technologies with other government agencies and commercial space ventures who also are partnering with us and collaborative efforts, and I'll be talking a little bit about that. Of course, NASA is always interested in our technology investments having spin-offs, and we recognize that our investments in nuclear technologies have benefits to the nation in terms of our space leadership, our national security, our global competition, as well as our investments with commercial industry is providing benefits to the domestic economy and has spin-offs for green energy. Next slide. So I'll start talking about the most pedestrian of the technologies, and pedestrian in the sense that we've been developing and flying these systems for 60 years now. The first nuclear power system in space was a radioisotope powered thermoelectric generator flown in 1961 using plutonium-238 as a heat source. The natural decay heat from plutonium-238 is converted to electricity through various means. The standard way that we've been doing it for 60 years is with a static power conversion technology called thermoelectrics. We're also looking at thermal photovoltaics and thermionics as other static power conversion that might have increased benefits in terms of efficiency. But really what we're pushing in radioisotope power systems for the next decade and beyond is dynamic power conversion to really generate a multi-fold leap in terms of efficiency that can enable new applications of these systems. Next slide, Sunny. So with radioisotope power systems over the last 60 years, NASA has visited virtually all the planets. The only planet that's not currently on this slide is Mercury. Radioisotope power has enabled a visit to a number of these planets, as well as operations on the surface of Mars. And we'll talk about that in a second. 30 missions so far on NASA's slate that have been enabled and enhanced by radioisotope power systems. So the current missions that we have that we'd like to highlight, of course, Curiosity is still operating on Mars, and Perseverance is the next build and the next phase of rover technologies that's operating on Mars since its launch in July of 2020 and landing in February 2021. The goal of Perseverance is to seek signs of ancient life and collecting rock and soil samples that will eventually be returned to Earth by the Mars Sample Return mission, which is currently being planned. We have a radioisotope power systems program, which I'm not really highlighting, but the purpose of that program is to really build these technologies and enhance these capabilities for our future. And with the support of that program, we were able to provide the multi-mission radioisotope thermoelectric generator, or MMRTG, to the Perseverance mission under budget, ahead of schedule, and above our power requirements, all happening during the COVID-19 pandemic. So that is a significant benefit of the program and what we really are looking to build on those types of successes for our future capabilities in space. The next mission that we're highlighting is the Dragonfly mission. It will be a flight of a quadcopter in the atmosphere of Saturn's moon Titan. It's planned for launch in 2027, again enabled by an MMRTG that will provide the power to charge batteries, just like Curiosity and Perseverance. The radioisotope power system is there as a long-term energy source or power source that charges the batteries, and the batteries are really what these systems operate on for their peak power loads. Next slide, please. So the current stable of capabilities in the RPS program that we provide include heater units or lightweight RHUs that provide about 1 watt thermal of heat that are used to keep systems warm. And these systems have been flying since the 1990s on missions such as Galileo, Cassini, Ulysses. And we're really going to be looking to these for our future. And NASA is working with the Department of Energy to restart our production of these heater units, because we recognize how important these heat units are going to be for survive the lunar night and even operate during the lunar night capabilities that NASA is now focused on under Artemis. Our MMRTG, or multi-mission radioisotope thermoelectric generator, is now flown two times on Curiosity and Perseverance, and soon will fly its third flight on Dragonfly, and will be a system for our future as we need it. But we're really looking beyond the MMRTG in terms of enhanced capabilities. The dynamic radioisotope power system using Stirling power conversion will be a workhorse for our future. And we envision that that's going to have lots of benefits on the moon, including enabling other isotopes beyond plutonium-238 to be used practically. And our next gen RTG is really back to the future. It is going to be a rebuild or a build a print, hopefully, of the GPH RTG that was so successful on Galileo, Ulysses, Cassini, and Pluto New Horizons. Next slide. So why do we look for efficiency? Well, one of the reasons primarily is the limited availability of our heat source material. And for the same amount of plutonium-238, we can fuel 3 to 4 MMRTGs, or equivalently 1.5 to 2 GPHS RTGs, or the next gen RTG as we're calling it, or perhaps 4 to 6 of the dynamic radioisotope power systems. And so if you look at that in terms of 1 unit per mission, that's 4 to 6 missions of power, of equivalent power, versus 3 to 4 with the MMRTG, and also much more power on those missions as well. Transitioning now to what we're doing in fission in terms of our technology investments. We're looking at fission surface power to provide sustained long duration surface operation at any lunar location. So enabling NASA and the international community to explore beyond just the North and South Pole regions where we might have peaks of eternal light from the sun, to being able to explore the entire surface of the moon and survive and really operate and thrive during the lunar night. We will be establishing this power system not only for the moon, but as an evolvable technology that will be able to transition for Mars exploration as well. And in terms of getting to Mars, we recognize that traversing that increased distance is going to require advanced propulsion beyond the state-of-the-art chemical propulsion technologies that NASA has relied on for decades now. So we're advancing these fission systems for both nuclear thermal propulsion and nuclear electric propulsion options that will allow NASA to send astronauts to Mars, hopefully in the next decade or two. So I'll focus on these technologies next, but I wanted to highlight the fact that NASA is working with industry and other government agencies in terms of partnerships on these technologies. I've highlighted the Defense Industrial Unit. We're working with DARPA on their Draco investment in the nuclear thermal propulsion demonstration, and hopefully that demonstration can benefit NASA's interests as well. We're also developing a partnership with AFRL on nuclear electric propulsion that can be a stepping stone to the larger systems that we'll need for human exploration. Of course, we're working with the Department of Energy, using their facilities for materials and testing and for fuel manufacturing as part of this whole initiative. Next slide. One of the innovations that's happened over the last 5 years or so is the federal government has made some improvements in terms of policy. And those improvements are streamlining our ability to pass launch approval for nuclear systems in space. Launch approval has also always been a burdensome, expensive, and a time-consuming process. And the new NSPM 20 establishes quantitative measures of risk by which it clarifies how NASA and now other government agencies can utilize these systems and pass them for launch approval. But also, more importantly, both NSPM 20 and Space Policy Directive 6 open the door for both commercial development and commercial use of nuclear power and propulsion in space. And we believe that that's an important next step. And we're looking to the future where in the past we had commercial venture really revolutionize Earth to orbit transportation capabilities with technologies such as SpaceX's and Blue Origin's. And we're looking for the same type of innovation to enter into nuclear power, both power and propulsion capabilities for the future from those commercial innovative ventures. So what we're doing with fission surface power is developing a 40 kilowatt lunar fission power system for delivery to a launch site or to a landing site by 2029. The design, as I mentioned earlier, will be extensible to Mars missions. The current scope of the project includes, right now we're working on conceptual design work with 3 vendors. And we're going to be down selecting to 1 or more vendors who will develop a ground demonstration unit and eventually be able to develop those units as a flight system to be launched in 2029. The transition to flight technology development and demonstration will be in what we're calling our phase 2 of our industry solicitation, which will be happening over the next year. And the Department of Energy is managing these contracts under the leadership of the Idaho National Laboratory. Next slide. With this 40 kilowatt power system, we're hoping to put it on the surface of the moon to support surface operations, where we might be exploring the ability to use in-source resource utilization to build habitats and mine for other resources on the surface of the moon, and also support the power needs of the human community that will eventually be on the moon in their habitation. The system will be, as I mentioned, 40 kilowatts. It'll have a 10-year life. The goal of the solicitation is to develop a system that will be less than 6,000 kilograms in mass and be capable of being transported on a lunar rover to an emplacement site will operate for its 10 years of life. In terms of nuclear propulsion, we're investing in both flavors, nuclear electric and nuclear thermal. The goal of the nuclear electric propulsion technology will be a multi-megawatt system using high assay low enriched uranium as a federal policy to prioritize the use of HALEU. We're investing in the technologies that will hopefully enable HALEU to meet our performance goals for this system. HEU is still on the table if the HALEU technologies prove unsuccessful, but right now the focus is HALEU. The plan is to use high efficiency Brayton power conversion to produce as many as perhaps 1 or 2 megawatts of electricity to support electric propulsion with 100 kilowatt or greater class electric thruster systems and the associated technologies that are needed to transport and process that power. An important part of both NEP and nuclear thermal propulsion is the cryogenic fluid storage. In the case of the NEP system, as we recently studied in our Mars Transportation Assessment Study under NASA's leadership, we determined that an advantage for nuclear electric propulsion is to use it with chemical propulsion. And so the baseline design uses a LOX methane chemical propulsion stage. That LOX methane has to be maintained under cryogenic conditions. But with that high thrust capability married with the low thrust capabilities and the high efficiency of electric propulsion, we found that to be a very advantageous way to transport humans and cargo to Mars. Also looking at nuclear thermal propulsion. In this case, we're looking at 25,000 pound force engines that would be used in clusters of 3 or more to transport the human transportation vehicle to Mars. That translates to multi-hundreds of megawatts thermal of a nuclear reactor core. Again, the plan is to use high assay low enriched uranium under federal policy, but HEU is also on the table if the technology proves insufficient. We're having to operate these fuels at extreme temperatures, 2,700 degrees Kelvin, in order to achieve 900 seconds of specific impulse. And so that drives a lot of research into reactor materials and the manufacturing technologies necessary to build and operate these cores. We're going to have to test these cores on the surface of the Earth before putting them in space. And so that just testing these cores is going to be a challenge. It's something that we did in the 1960s in the open air in the Nevada desert, but that means is no longer considered a feasible means to test these systems. So we're going to have to design the test facilities to do this. And of course, cryogenic fluid storage of hydrogen, in this case, a much greater challenge than LOX methane, is really critical if you want to achieve the performance potential of nuclear thermal propulsion. The HALEU solid solution fuel that we plan for this engine will achieve 900 seconds with 2,700 Kelvin temperature. The plan is to, right now we're exploring a plan to work with DARPA and Draco that will be developing a subscale nuclear thermal rocket engine with an eye towards being able to scale up that engine to the 25,000 pound force target with minimal technology. Hopefully that will be able to scale up with just engineering. We really need to get to that 900 seconds of specific impulse to meet our performance goals for Mars. As I mentioned, we'll be performing integrated ground testing of this system, and developing those ground test facilities is going to be a part of this project. And we're working with other government agencies in partnership because we recognize these challenges are shared challenges for developing these systems. Of course, between both fission, surface power, nuclear thermal propulsion, and what we hope to be awards for nuclear electric propulsion in the near future, we have a number of partners that we've awarded contracts to, and those partnerships are listed on this screen for all your interest. Of course, cryogenic fluid management, as I've already mentioned, is a critical part of both NTP and NEP performance goals. And we intend to chase the cryogenic fluid management technologies through tipping point public-private partnerships operated out of the Space Technology Mission Directorate as near-term solicitations. So with that, that's a kind of a snapshot of the fission and radioisotope power technologies that NASA is currently investing in. And I'll leave it there for any questions or discussion if you'd like.
Lynn, that was great. You know, when I look at this thing, it makes me think about people carry around pictures of their children in their wallets. I might carry pictures of this kind of stuff in my wallet. I didn't want to see my kids. I'm just kidding. Hey, one question before we pop over to the first talk of the day, right? I remember when you and I were working on the Nuclear Systems Working Group back when NASA was kind of thinking about some prioritization of nuclear stuffs. If I remember correctly, the safety timeline in the previous governance was a 5-year period minimum once you knew exactly what you were going to buy and the president, what you were going to build, and the president had to sign it.
That's correct.
Does the president still have to sign it under the new governance, or have they changed the governance?
They've changed the governance so that now there's 3 tiers.
Yeah.
And based upon the risk posture of the system, and that requires a degree of analysis that's still going to take years, but it's not going to take the 5 years as it had in prior. If you can qualify for tier 1 or tier 2, you do not need to go for presidential signature. The approval process stops at the administrator of NASA in this case. Or if it's a commercial launch, it would be the Secretary of Transportation. The only systems that would need to go to the White House for approval would be the use of highly enriched uranium, which still is on the table if we need it, and those systems that have high risk of public exposure.
Got it. Cool. Awesome. That's great. Thank you, Glenn. Really appreciate you coming and chatting with us today about all things nuclear. And glad you get a chance to join us here today for our presentation stuff. So
I'm looking forward to it.
Yes. I'm going to stop sharing. All right. So I believe first up, we have a presentation by Professor Andreas Hein from University of Luxembourg. He'll be talking to us. The title of his talk is Extremely Lightweight Solar Sails for Fast Deep Space Missions. And so, Andreas, you should be able to share, and you have the con. And I'll give you a 3-minute warning.
Okay, I don't think I have the right to share.
Okay, stand by.
Right now.
I will click one more thing. Now you should be able to share.
Yeah, now it works. I hope you can see the screen. Just putting it full screen. Okay, can you see it?
Yes, we see it full screen.
Okay, great. Yeah, thank you very much to the Limitless Space Institute for having me, and also for the possibility to pursue this project over the coming year. This talk is going to be about ultra lightweight materials for drastically improving the performance of solar sails. Now, most of the team is coming from the University of Luxembourg, and maybe for most of you, you've never heard about the University of Luxembourg. So the University of Luxembourg is the only university in Luxembourg. Luxembourg is a relatively small country. It has recently been founded in 2003, but we have about now like between 7,000 and 8,000 students. So it's a fairly large university. Now, our team actually comes from different organizations within the university. So I'm from SNT, which is the Interdisciplinary Center for Security, Reliability, and Trust. And one of my colleagues is coming from the Faculty of Science, Technology, and Medicine, FSTM. So it's a kind of collaboration between different organizations within the university. I'm the head of the Space Systems Engineering Research Group. Our focus area is systems engineering applied to different areas of space, for example, service-based space systems design, miniaturized space systems, and space resources and space manufacturing, where Luxembourg is currently heavily investing in. We also have two facilities under our management. The first one is the concurrent design facility, which is also going to be used within this project to design new space systems. And we also have the CubeSat lab, where we are designing and prototyping miniaturized space systems. So this is our team. It's fairly new. The team was founded about a year ago, but there's already a decent number of team members who have joined us so far, and hopefully the team will grow in the future. Now let's get to the lightweight solar sails. Most of you are probably familiar with the working principles of solar sails. In a solar sail, you have a surface, a sail, which is typically reflective, and the light from the sun is impacting that surface area, and in addition reflected, and thereby that sail, as a sail on a ship, is pushed forward and accelerated. This can be expressed by this equation, which expresses the force acting on the sail in relationship to P, which is the solar radiation pressure, the photon pressure of the photons coming from the sun, multiplied by 1 plus R, where R is the reflectance. Typically, those sails are as reflective as possible, and divided by the speed of light. And on the left-hand side, we have the mass of the spacecraft multiplied by the acceleration of the spacecraft. Now, if we look a little bit deeper into the mass can be subdivided in the mass of the payload and the mass of the sail itself. And if we further look into the mass of the sail, this can be expressed as the surface area of the sail multiplied by delta, which is the mass per area of the sail. Now, if you look at this equation, you have two possibilities to optimize or to tune a solar sail. So you can either increase the reflectance of the sail, but then there are certain limits to it because you cannot go higher as one, or you can try to reduce the mass of the spacecraft. So you can either reduce the mass of the payload or reduce the mass of the sail. And if you want to reduce the mass of the sail, typically what you want to do is to reduce the delta, the mass per area. And this is the strategy we are going to pursue in the following. We are trying to reduce delta as much as possible in order to increase the sail performance. Now, how can we do that? One exciting recent development is in the area of ultra lightweight materials. And one of these materials is aerographite. Aerographite has been discovered about 10 years ago, and it's considered to be the material with the lowest density in existence. You can see a bulk aerographite piece here. It's this darkish black piece here. If you look deeper into it or closer to it, then it has a very peculiar microstructure. In this case, it has this microstructure made out of tetrapods. It could also be a different shape, but here in this case, it's tetrapods. And these tetrapods are interlinked and forming this kind of foam-like structure. Because it turns out that if you would squish and deform a piece of aerographite, it actually returns to its original shape. And this can be seen here in this stress-strain curve. You can see here that if you would put a load on aerographite, it would actually come back to almost its initial shape. So it's to a certain extent, its shape preserving. Its density is really the lowest of existing materials, 0.18 kilograms per cubic meters. And if you compare that, for instance, to aluminum, it's a factor 10,000 lower than aluminum. So it's extremely lightweight. So essentially, if you imagine you have a kind of box like 1 cubic meters, you could basically push that box up with one hand. So to summarize, aerographite, it has an extremely low density. It's a foam-like material, meaning that there's a lot of space in between these tetrapods or other microscopic elements. And in terms of mechanics, it's a so-called stochastic porous network structure. Stochastic because the way these tetrapods are interlinked is somehow stochastic, somehow random. And it's porous because you have a lot of space in between these tetrapod elements. And this leads to these particular, very peculiar material characteristics. Now, can we use aerographite as a material for solar cells? This question has been addressed already by Heller et al. In 2020, and they propose a solar cell made out of aerographite, a spherical solar cell about 1 meter in diameter, and they do some basic analysis of what would happen if you would deploy these cells in the orbit of the Earth or closer to the Sun. It turns out that because of the low density of aerographite, the performance is quite phenomenal. You can see here that if you would launch this aerographite sail at the distance of 1 AU, so at the distance of the Earth, you would almost immediately reach escape velocity from our solar system. If you would go closer to the Sun, the velocities become much more phenomenal. Here you can see that the velocities are on the order of hundreds to thousands of kilometers per second, which means that you easily get on the order of a few % of the speed of light. If we translate that to the travel time to Proxima Centauri, you can see here that travel times between 1,000 and even down to 100 years would become possible with that material. Now, the question is, of course, how mature is that technology at this stage? Because we have this paper which does this basic analysis, and it turns out that because this is a first order feasibility analysis, we should consider, or we should take it as a proof of principle. So it's something in the range of TRL1, I would say. However, there are a few gaps we need to address in order to really find out whether aerographite sails are feasible, and we have to dig deeper into the engineering. First of all, is it feasible to design thin, few micrometer aerographite sails? Because if you look at these charts, the best performance can be achieved with sails which has a thickness of about 1 micrometer, so which is extremely thin. And if you compare that to the slide before, those tetrapod structures, you really get on the order of the tetrapod structures. So can we actually design a 1 micrometer sail? This is an open question. We also have to take into account all the other subsystems of the spacecraft, like power generation, communications, etc., because the way how we integrate these subsystem components into the overall spacecraft will determine whether the material stress which is emerging and the mission overall becomes feasible. Yeah, we have to integrate these systems. So in order to address these gaps, we have proposed Project Elvis, and our objective is to get from where we are today, from TRL1, from the state of the art, up to TRL3. And we would like to do that by addressing the following 3 objectives. The first objective is to assess the feasibility of these micrometer scale aerographite structures. Can we actually design such structures? And the second one is based on objective 1. Can we actually design feasible sail designs at the micro scale? So Heller et al. Proposed this spherical sail, but there are many different alternatives for how that sail design might look like. And we might come up with fairly unique sail designs because of these peculiar characteristics of aerographite. And the third objective here is to come up with feasible system architectures or configurations of the sailcraft and how these different subsystems such as communications, power generation, etc., can be integrated into the sailcraft in order to achieve its mission performance. These three objectives are somehow interrelated, and you can see here that we are starting at the microscale and go gradually up to the macroscale to the entire spacecraft system. Now, what is the methodology to address these objectives? In order to address objective 1, we are using multiscale simulation, where my colleague Lars Speaks has worked on for a long time, and we are trying to assess the feasibility of these micrometer scale aerographite structures. We will then use sail geometry design in a CAD tool and use finite element analysis to come up with feasible sail designs which can withstand the loads during the mission. And finally, we are going to use trade space exploration and concurrent engineering in order to identify the feasible spacecraft architectures and configurations. Now, because these different objectives are interrelated, this is also reflected in how the work packages interact. And you can see here that there are various interactions between the microscale and the macroscale structure of the spacecraft and the sail. So we would first start with simulating the scaled down aerographite structures, and then in parallel come up with feasible sailcraft architectures, and then combine those in work package 2, and there will be a lot of interactions between the sail designs and the overall spacecraft sailcraft architecture. The consortium consists of experienced researchers such as Lars Speaks, whom I already mentioned, who is coming from computational mechanics. My background is more from spacecraft systems engineering. Lavinesh Rana from my team is an expert in concurrent engineering, and we have already recruited our first intern, and we are also supported by a volunteer. So to conclude, aerographite seems to be a very promising material for designing sailcraft, and which might have the potential to increase the velocity by a factor of 1,000 compared to currently existing spacecraft. But it requires a feasible design for the overall spacecraft and the feasibility of micrometer scale aerographite structures. Hence, our objectives are the following three. We would like to go from the microstructure, feasibility of aerographite at the micrometer scale, up to the overall feasibility of the spacecraft system. And with that, hopefully, maybe this project or one of the other projects we're going to see today is really going to enable interstellar travel, and maybe fascinating pictures are going to be returned to Earth in the future. So I'm looking forward to an exciting future. Thank you very much for your attention.
Hey, thank you, Andreas. I appreciate it. Very good presentation. Some interesting, thought-provoking stuff. There may be some questions for you during the Q&A. I'm going to make one observation that Lynn and I were talking about when you showed us that density of this aerographite. If you make a solid with that kind of a density, that's actually lighter than the density of air. So, you know, would you have to be careful where you put it down, because it wouldn't stay down, right? It might just float up to the ceiling or something like that.
Yeah, so this is something which is frequently addressed in articles which are like in the press. So the reason why it would not fly into the air is because it has this very porous structure, and it's actually it's basically consists of air, yeah, and then you have like the graphite. So that's the reason why you end up with these very low densities. However, if you would put it into vacuum, then of course that would be different, and you would be left with the graphite. Yeah. However, this is an interesting point, because actually one of the things you have to be very careful with, and for instance, Martin Timer from TU Dresden has actually worked on the issue of outgassing, because the air is actually captured into these tetrapods, and you have to be very careful with outgassing effects if you put it into space. Yeah.
That's interesting. That might be a bad day, right? Yeah. Good stuff. Hey, thank you, Andreas. I appreciate it. We'll come back with some more questions here in a little bit, I think. Next up, we have Charles Chase from Unlab, a partnership with Technion Israel Institute of Technology and UCLA as well. The title is Asymmetric Potential Vacuum Fluctuation Force Experiments. So Charles, you have the con, and feel free to share your charts.
Okay. Let's see. Can you see my screen okay?
I see, yes, I see your smiling face, and Yuval and Jim and
Oh, okay, great.
and we see your charts full screen.
Okay, wonderful. Yeah, welcome everybody. And, I just wanted to thank you, Sunny and the Limitless Space Institute for sponsoring us. We've been good friends and colleagues for a long time. Very exciting to see all the different work progress. And we really welcome this opportunity. We have quite a spread out team today. Yuval is in Israel, of course. Yuval and I first met at one of our first advanced propulsion and energy conferences at MIT. And we've been colleagues and friends ever since. Jim Jimjeski from UCLA is currently in Japan. So quite the range all the way from Israel to Japan. Jim and I have worked together for many years, back from when I was at the Lockheed Martin Skunk Works. And again, another dear friend. And Ami Shand, who Jim introduced us to, runs Applied Nano Structures, App Nano. He's in the Bay Area, which is where I am today, actually. And he's going to be building devices for us. And so I run the Unlab, which is a nonprofit. And we are all about developing breakthrough technologies that can really change the world. And I think what we're going to talk about today is one of those technologies. So let me see if I can go to the next chart. There we go. So what we're thinking about and working on is how to generate forces by interacting with vacuum fluctuations. Goes by many names: the quantum vacuum, 0-point energy, the vacuum ground state, in electromagnetics, the continuum. And so just a little background for people who are not familiar with vacuum fluctuations. They come from if you look at quantum mechanics, it's the ground state of the quantum harmonic oscillator. Of course, in Planck's law for black body radiation, is dependent on the quantum vacuum fluctuations, the ground state. Can you see my cursor when it moves, or does that not show up?
Yes, we can see your cursor when it moves.
Oh, okay, great. And of course, the Casimir force, when you have plates close together, there's a force between them. It's because of the modes of the vacuum that are excluded is how that's explained. Very large forces, actually. So pressure of 1 atmosphere for a 10 nanometer plate separation. And in quantum chromodynamics, mass is shown to come from 99% of a proton's mass is from quark and gluon vacuum fluctuations. We typically only talk about electromagnetic vacuum fluctuations, but there are also other vacuum fluctuations that exist. And so you can model this very easily with fluctuating dipoles, the fluctuation dissipation theory, and going from van der Waals forces, which are just interactions between individual dipoles, to Polder interactions, which is a dipole and a surface, to Casimir interactions, which are two surfaces of dipoles interacting together. And there's many observed phenomena attributed to vacuum fluctuations, like spontaneous emission, Casimir forces, the Lamb shift, noise in quantum systems, also bond energy. You need to take into account vacuum fluctuations to accurately calculate that, and of course mass. But want to point out that you can derive the Casimir force and lamp shift without ever invoking vacuum fluctuations. So you can use a radiation reaction calculation versus a source field. It depends upon the ordering of the operators in QED, and you can derive Casimir force without invoking the vacuum. And then, of course, there's the conundrum of the vacuum energy of free space based on the cosmological constant versus what you calculate from QED. If you use the Planck scale cutoff, it's 120 orders of magnitude difference. So, you know, do vacuum fluctuations really exist, and can we use them? Well, you know, if we want to generate forces from vacuum fluctuations, if you assume that the vacuum has translational and rotational symmetry and you're in thermal equilibrium, there'll be no net force or torque. And that's independent of your physical model details. It's a simple free energy calculation. So you need to break one of those assumptions. You either have to not be in thermal equilibrium or you have to break the symmetry. And so you can, and so such a system like we're talking about, an asymmetric potential, you know, breaks the symmetry. And, you know, it's also interesting to note that in curved space-time, the vacuum will not have translational symmetry. So in curved space-time, the effect is probably really small. And also curved space-time is not in thermal equilibrium, as you see with the Unruh effect, which has recently been measured. So, you know, essentially, we are never actually ever in symmetry or in equilibrium. And so our approach, getting to what our approach is, we are looking at using asymmetric potentials such as exist in a resonant tunneling diode to interact with the vacuum and cause a force on the nanostructure. And so this would enable propellantless propulsion. So the propellant you're working with is the vacuum itself. And it would also enable acceleration to near light speed, limited, we think, only by vacuum friction itself. And so let me, if you look at, these are some calculations that we've done in the previous LSI grant that we have, where we're looking at a comparison between an asymmetric and a symmetric situation. And what's calculated here is the wave function, and we're showing the probability size squared. And you can see on the top is a symmetric wave, and the waves are incident in both directions. And the probability of finding the wave on either side is symmetric in the symmetric situation. Now, if you go to an asymmetric structure, such as you would find in a resonant tunneling diode, you see that the wave function itself is not symmetric on either side of the barriers. And so conservation of momentum requires that there'll be a force here because of this difference in the probability of finding the wave on either side. And so these sort of structures, of course, have been built. Resonant tunneling diodes show some examples here. Here's a heterostructure double barrier, you know, kind of a 1.2 nanometer dielectric separation between a semiconductor. Here's a photon assisted one out of Sandia. And here's a triple barrier resonant tunneling diode that they made into an array. This is actually the one that we use for our calculations when we use the field inside the structure. And our hypothesis, backed up by our analysis to date, shows that this would generate a force. So here's a little cartoon here. In this case, because of the orientation, there would be a motive force on an array of these devices. And in this case, the force would be in this direction because of the way that the tunneling happens in these structures. And again, we would have a force in this direction. This, of course, is controversial and would change everything if found to be true. Now, I'm going to give a little background on some work that's been done with vacuum fluctuations that leads us to believe that what our analysis is showing us could be correct. On this side here, you have some work by Garrett Modell, professor at UC Boulder, Colorado. And so he showed that with an asymmetric optical cavity, like a Casimir cavity that was on one side of a metal insulator metal resonant tunneling diode, that he generated a current which he believes is clearly from vacuum fluctuations. And it depends on the size of this cavity. He's done extensive measurements of this and showed a decent current generated from the structure. He does have a patent on this as well. Another example is this graphene that vibrates at thermal equilibrium and generates power that they also attribute to vacuum fluctuations. So these are a couple of examples out there where we may be seeing currents and forces from vacuum fluctuations. And so it also appears that the symmetry of the vacuum can be changed. And what I'm showing here is a prediction using the world line method, not fluctuation dissipation, but the world line method, which was first pointed out to us by Sonny. And this is showing the vacuum fluctuation distribution between a sphere and a plate. And you can see it is the symmetry of the vacuum is asymmetric based on the structure. People have measured inside cavities using emission from an atom, from a single atom, the spontaneous emission from a single atom. The shape of the vacuum inside the cavity is also asymmetric. And then our colleague Shanhui Fan has shown analytically by changing the potential between the chemical potential with semiconductors, you can control the attractive and repulsive force of the vacuum. And people have also studied the Casimir force and how it changes between metal and anisotropic materials. So it appears that the symmetry of the vacuum does not have to be uniform. And people have also shown that you can couple to the vacuum. So that's very important for our concept, because we are assuming that the wave, the electron wave that's propagating through our resonant tunneling diode is coupled to the vacuum and can couple to the vacuum. Well, here are some examples of direct sampling of electric field vacuum fluctuations, where by controlling both the time and space of their measurement, they were able to determine the magnitude of the vacuum fluctuations that were coupled to their probe. So they had a probe here, and by controlling the time and the space, they were able to measure the vacuum directly. And here's another example, again using a probe, but this time in a crystal. So by coupling to the vacuum fluctuations in the crystal, they were able to determine what the characteristics of the vacuum. And then also in chemistry, you can change the conductivity of semiconductors based on how it interacts with the vacuum. So, and here's some measurements associated with this. So these are three examples where the vacuum has coupled to the virtual photons that are the vacuum. And virtual is a really lousy name because these virtual photons do exist for a certain amount of time, governed by the Heisenberg uncertainty principle. So, you know, they're real, but only for a certain amount of time. And these have all shown coupling to them. And so to analyze our approach, we built upon some work by Lawrence Ford. He's from Tufts University, and he's been analyzing radiation pressure from quantum fluctuations. And, this is the approach that we used in order to model the sort of forces that we can generate. And just a couple of things that he's been able to show in his work is that the vacuum fluctuation pressure increases barrier penetration. So you get more tunneling when you increase the vacuum pressure. So that's a direct effect there. Excuse me here. And then he also showed that the velocity fluctuation of an atom from vacuum fluctuations was greater than the thermal motion at low temperatures or that resulting from photon recall. So it's very interesting the amount, size of the effect that can happen from vacuum fluctuation pressures. And so we've used his approach, and we took into account the experimental data from these resonant tunneling diodes that I showed previously, the internal field, and excuse me, we use that to calculate what sort of force can we expect from these structures. And from a single diode, we get a small but definitely a very measurable force. Forces have been measured much smaller than this, about 2.3 piconewtons per diode. And our assumptions are that the field in the resonant tunneling diode is coupled to the vacuum fluctuations. We think that's a fair assumption based on some of that previous literature I showed. We're also assuming that the coupling lasts longer than the transit time through the resonant tunneling diode. And of course, tunneling time is people have measured it. There's quite a bit of debate about how long that actually takes. I think you can use the uncertainty principle to determine how long the coupling is going to last at a given energy. That's what Garrett Modell does. And in this particular calculation, the reverse modes have been neglected, although as you see in the full quantum mechanics calculation we did of the wave function, that incorporated both reverse modes and the forward modes as well. And with both those modes, we saw the asymmetry in the wave function. So we think that's a fair assumption. And just to do a rough calculation, we said, well, we get 2.3 piconewtons per diode. Well, what if we have an array on a small wafer, and we thin that wafer down so the weight is really low? We assume a 10% coverage of the array with the diodes, and we get a force that's really quite large, of 9.3 newtons per kilogram, really quite a large force, which would be just amazing if we can show that happens. And I just wanted to point out that, above 7 terahertz, if you look at the Planck black body, above 7 terahertz, vacuum fluctuations dominate at room temperature. So either getting to very high energies or getting to low temperatures. At about 50 degrees K, the vacuum fluctuations dominate above 1.5 terahertz. So it's interesting to consider when the vacuum fluctuations will be more prevalent or have more impact than the thermal fluctuations. We've also considered, and I won't go over this too much, the vacuum fluctuation forces between dielectrics. We think that there's a potential for even asymmetric materials to have a force between them because of the way that the vacuum interacts differently with different material properties. And so under this current program, we're going to be building some devices and measuring some forces. I just wanted to point out that the Casimir force experiments measure attractive and repulsive forces, not motive forces. As far as we know, no one has ever tried to measure a motive force from these structures. I don't know, why would they? Because who would think that this would actually happen? But
Charles, this is Sonny. You have 3 minutes.
Okay, thank you. I'm almost done, I think. And so this is the standard sphere plate measurement. People have made nanostructures. This is a great review by Jeremy, actually, of the different sort of measurements, but no one has measured motive forces previously. And so that's what we're off to do. Working with Jim Jimjeski at UCLA, he has a low temperature, ultra high vacuum, AFM, STM in his lab. We're going to be building structures on cantilevers and measuring them as a function of orientation and temperature. These are the ones: symmetric cavity, asymmetric cavity, dielectrics, potentially going to chemical potentials. And then we're going to design these resonant tunneling diode approaches. So this is what we're going to be able to get through under the program. And here's what these structures look like. We're going to compare symmetric to asymmetric, different geometries and different materials. And these are the resonant tunneling diodes that we're going to work on designing the process for how to build these on a cantilever. These are, we have a good idea of what we'd like to see. And, you know, ultimately, we wonder if, in addition to the diode, maybe we would like a terahertz coupler with a ENZ terahertz waveguide going to the diode, and then with an optical Casimir cavity to give us a negative vacuum fluctuation pressure would generate the largest force. So that's kind of the ultimate concept. Here's the program with the milestones. You know, Ami is going to build the cantilevers with the devices for us. We're designing the experiment at UCLA, and then we'll do the motive force experiments here and work on the RTD fabrication design process. So that's a quick overview of the program, and hope it made enough sense. Let me see if I can stop sharing there.
Charles, great presentation as always. Love to see a lot of the rich background, some of the different things related to some of the topical discussions in the domain. So thank you for that. And Adam K, I pulled you in as a panelist because I know you'll be presenting later. So hope you. I saw you were in the attendee list, so I just popped you up to panelist. So good to see that you joined us. Hello. Let's see. Next up, we have Professor Richard Norty from Delft University of Technology over in the Netherlands, and he is he will be giving us a talk on his project titled "Real Acceleration and Impulse Limits of Light Sails." So, Richard, you have the con, and I'll reset the timer and look forward to hearing what you have to say.
Can you see my screen properly, or the presenter mode?
I think we're seeing the presenter mode. You've your presentation. You can pick which monitor that it goes to presentation on. So,
1 second here. There it is.
You'll probably have to exit out of presentation first, and then go into your PowerPoint. Okay, there you go.
Yeah. Okay.
Awesome.
Great. Perfect. Thank you very much. Yes. So thanks everyone. Thanks, Sunny, and thanks to the Limitless Space Institute for this really amazing opportunity. So I want to give, I guess, a bit of an overview about the project that we'll be working on for the next 2 years through a fellowship grant at the TU Delft in the Netherlands. And here, what we've been really looking at is really ultralight light sails for space exploration. And so I always like to give this little bit of a overview or infographic, because it's kind of neat to see how much we've really explored the universe as humans in the last 64 years. And you can see that we've made, quite a bit of trips to the moon, quite a few trips to Venus and Mars. But if you go out really a little bit further, it starts to really dwindle down to just a few missions. So you have these really amazing long-term missions like Voyager 1, Voyager 2. And if you really look at the kind of scale that we need to traverse to really get this Alpha Centauri, we're all part of the same goal, looking at the same challenge, which is that it's really far to get there, and it would likely take us something on the order of tens of thousands of years to really start to explore this part of space. And so one thing that's really inspired me over the last few years is in 2016, there was the announcement of the Breakthrough Starshot Initiative. And here the idea was to really be able to use gigawatts of laser power, shine it onto a 1 gram scale laser microchip satellite, and accelerate it to about 1/5 of the speed of light. So the idea would be to really bring down these times from 10,000 years to 20 years. And so I found that really interesting, kind of given the type of, I would say, different research that I was working on at the time. And I can say that one thing that attracted me about the sails was the different type of technology it was. So the idea really is to be able to miniaturize a chip, which has communication systems, cameras, microcontrollers, antennas, and essentially attach it in some way, which is still not clear, but some way integrated into a light sail. So essentially a 4x4 meter sail, which is somewhere on the order of about 1 gram. And I think we always kind of lose sight of what 1 gram is, but a US penny is already 2.5 grams, and we're thinking of something that's 4x4 meters. So you're just thinking of something that also needs to basically have nanoscale thickness in order to reach this kind of critical density. And if you do, and if you can reach this, then the opportunities are really exciting, because we can start to think about essentially using about 10 minutes of laser exposure to try to accelerate a sail to near about 1/5 of the speed of light. And so, this is a really big project. I think there's a lot of people working on a lot of interesting parts about this. For instance, how to miniaturize all of these components, how to make a sail, the laser systems. There's a lot of different aspects about this. But one of the things that I find most interesting is the light sails. And I think a lot of people find this to be one of the main great challenges of this compared to other technologies. And the reason for that is because now you're talking about a really different type of nanotechnology. And so if you look over the last half century, we've really been working on miniaturizing nanocomponents in X, Y, and Z, right? And that's really slowly going to actually, even Gordon Moore thinks this will end in 25. But we've been working on this over the last half century. So it's really going in line, miniaturizing things on the chip, and miniaturizing the microchip really go in line with a lot of conventional nanotechnology. But I would say the sails are really something very unique, because you now want something that is really macro sized in X and Y and nanoscale in Z. And I think that really sets it apart from different types of technology that's needed for this mission. And so optomechanics is actually already, this is the field that I was working in when I first saw this announcement about Starshot Breakthrough. And optomechanics has already really started to pioneer a lot of these type of nanotech. And just to give you an idea of how that works, if you look at optomechanics, it's really the idea of using a movable mirror integrated with an optical cavity to make ultra-sensitive measurements, and to even do a preparation of macroscopic quantum states with these mirrors. So really looking at the quantum signals of these movable mirrors. And one of the challenges is that at the end of the day, these mirrors need to be attached to something, to some environment, whether it's a chip or some kind of experiment. And that experiment's going to have some thermal noise to it, say if it's at room temperature. And that thermal noise essentially can essentially start to leak into your optomechanical measurements. And so one of the neat techniques that the community has really come up with was to essentially make the most 2D mirror you can think of, which is essentially a membrane mirror, which is punctured in holes to make it more reflective. And this essentially has the minimal amount of real physical clamping to the outside environment. And so the field of optomechanics has really already been looking at a lot of the same stringent requirements. They also need high aspect ratios, very thin sub-wavelength thickness of the mirror. They need high reflectivity, and they also want low absorption. So it was for me really interesting to see that this is also a challenge for space flight. So how do we design these mirrors? Essentially, we will take a membrane, which is 50 to 200 or 300 nanometers thick, so really sub-wavelength thickness, and puncture it with holes. And the idea is, and this is kind of essentially a counterintuitive idea, that by punching holes into it at the nanoscale, we can make an ultra-reflective metamaterial. So this is more or less what a 3D kind of rendering of what one of these trampolines looks like. So it's a little membrane trampoline, which has been punctured with holes to make it reflective. So without holes, we can see that we essentially get something on the order of about 30%, kind of along all the wavelengths. But if we are able to engineer a photonic crystal into it, we can make them ultra reflective in a way that constructively interferes with the incoming light and destructively interferes after it. So essentially making a mirror. And this is really quite reflective over a very specific wavelength, which we can tune just by changing the size of the holes. And specifically, one of the materials that we're looking at is silicon nitride, because if you really look compared to other types of reflectors, it's really one of the thinnest that you can make. It's been made at centimeter scale in our lab. We can get parts per million absorption. It doesn't wrinkle because it's under high stress. And so this really sets apart this material as really kind of one of the very few, and maybe if only one of the few materials that can really have the stringent requirements required by Starshot when it comes to reflectivity, heat management, these kind of things. But I still think there is quite a bit of engineering that needs to go into it. But I really think if you look at all the other materials, it's really quite one of the most promising ones. So just to see what these look like at an SEM of what these look like at a close scale. So it's just really a membrane punctured in holes, which have been lithographically made. You can see this is what it looks like when they're zoomed out a little bit more. So here's the average human hair. And if you zoom out a little bit further, this is essentially some of the largest photonic crystals that are usually being made nowadays. So something on the order of 350 to 350 microns is kind of some of the biggest photonic crystal reflectors that are made. And one of the things that now we're working on in our lab is really extending this out to really the centimeter scale. So here you can see the membrane I was showing you, shown in arrows, and this is essentially the type of suspended photonic crystal membrane structures we're now able to make. So this really starts to look like some of the really highest aspect ratio optical nanophotonic structures you'll really find anywhere. And here, essentially, we're really just limited by the cost of lithography, for instance. And it really has a lot of the things that you would want: high reflectivity. It's also low absorption. It doesn't wrinkle. And so one of the things that we've been looking at is essentially what can we see at the small scale that would allow us to really get some new vantage points here. So here the idea is that with these large scale membranes, it's really hard to make sweeps or make changes and really start to look at different aspects of these photonic crystals. I'll skip a little bit through this, but this is more just to say that silicon nitride is really now, I would say, one of the least optical absorptive materials. This is actually some work from my PhD at Caltech, where we were able to essentially interface and optically trap silicon nitride membranes with about double the power density now required by Starshot. So that in that sense, it means that we are in a good space in terms of optical power load that these types of materials can take. And so one of the things that we've been looking at is essentially now what you notice here is that the spot size is actually quite small, which is essentially how we get these photonic how we get these really high power densities. But if you really want to shine a laser on a photonic crystal, it can't just overlap a few holes, but it has to overlap many holes. And so that starts to make it quite difficult, because it means you need higher powers in order to have the same power density for the larger beam. So this has actually been a problem for us in a way that optical power is difficult to come by sometimes. But also that these high-powered lasers need to be tuned to a specific wavelength of the photonic crystal, and high-powered lasers are not generally a very tunable thing. So one of the things we wanted to do was essentially say, maybe we can look at another wavelength. So here's what a smaller scale photonic crystal looks like. So this is a 300 micron by 300 micron with some tether. So everything you see here that's not blue is a suspended structure. So here's a kind of a closer look, and this is all under high tensile strain. And you see that we make the membrane design all the way out to the tether. And so essentially what we were doing was we were thinking, why don't we just turn up the absorption by going to an absorptive wavelength and see if we can kind of get some new insights about the dynamics of these systems when they start to heat from laser light. So we had an optical detection system, and this is a little bit to give you a sense of what we were working on before and how we've kind of stumbled upon some new technologies just by looking at these kind of dynamics. And we could already see that somehow our laser was essentially driving up our membrane by really hundreds of times more than we're used to seeing. And what we were able to see is that we can actually get some dynamics in these systems that were caused specifically by the absorptive heating. So we can essentially start to drive these systems, start to really resonate these kind of small scale structures. And by having it go through an optical potential, you start to see really unique dynamics that actually have not been observed before. So what we would essentially see is this small sail going through very different types of optical potential. And what we got from this was that we started to see something equivalent to an optical frequency comb, a mechanical frequency comb. And it's a mechanical frequency comb that actually requires no feedback control, no precision optics, and is completely driven by one laser. So this is a really unique kind of physics that we learned when we were studying the absorption of these sails. And so I think this is something maybe people could take a look at. But it's really just to give a sense that, you know, we have these goals of interstellar travel, but I think when you have these lofty goals, you also start to stumble upon this other neat physics that you just would have never really stumbled upon, I think, had it not been for those lofty goals. And so now in this project for rails, we're going to be essentially really trying to take a neural. We've been working on a machine learning type of design of light sails. So this has been actually led mainly by a PhD in my lab, Lucas Norde. And essentially here, the idea is that people have been using topology optimization combined with neural network design to do different types of mechanical structures. So they have an image, you impart some force onto this physics, and you can really feed this into a neural network. And so here the idea is to really, instead of doing mechanical systems, really doing optical systems, something that looks like a sail. And so what we've been able to do is essentially take one of the big parameters that everyone really looks at in light sail design, which is acceleration distance. And this essentially tells you how little distance you need to accelerate to a certain distance to make a certain acceleration. So this has really been explored already in many other avenues. So people have really tried to essentially minimize the acceleration distance that you need given a different design. So you'll start to get designs that look something like essentially long strings, which might not be very practical when you really want to make a 4-meter sail, since these will only be really separated by 100 nanometers or so. And so we started thinking about that a little bit more and saying, we always make this assumption that we can easily accelerate to a fifth of the speed of light with 10 minutes of laser exposure. But these are some really extreme speeds. And so we started thinking about the actual strains that are actually made on these sails. So if you look at what a lot of these optimizers do is they try to just minimize the acceleration distance, but there actually might be a strain limit to how much you can actually accelerate something, and that's something that we wanted to start looking at, because formally what we were doing is we basically your photonic crystals came in two flavors, more or less. You would start to see something like a square lattice or something like a hexagonal lattice. And so one of the things that we started looking at is actually optimizing for costs, trying to see, can we make, for instance, bigger structures that are easier and more economical to make if we want to make really large scale sails. And what we found is that by putting in more constraints into our neural network optimization, we started to get really new lattices that really I haven't honestly seen very much in the literature, where you start to look at things that are more a little bit like quasi-crystals and overlapping structures. So things that have short range and both long range design. So you really start to see that once you start to put in more constraints, you actually start more realistic constraints of the missions, you start to get some very interesting answers. And so now one of the things we want to look at in Rails is to really say, what is this minimum or the real minimum acceleration distance that one could envision? And that's not just going to be about engineering the nanoscale unit cells, but really thinking about the large scale engineering of the sail. And that's going to make it a very...
Richard, 3 minutes.
Great. And so I think that's going to really make this a very interesting problem from the neural network optimization side, because it's really a new type of problem. We're not just looking at the nanoscale and saying, hey, what is the best unit cell with the best reflectivity, but also looking at the mechanics of the entire structure. So we think that that's actually going to come up with some really new insights, and we're quite excited to explore this. And then one of the things that we're also excited about is actually being able to produce this. So earlier this year, our lab received an ERC starting grant. So this is going to allow us to really make a new type of state-of-the-art system that allows us to bring fabrication and a high-powered laser into one system, so that we can really start to push the limits of what is possible in terms of a small-scale launch. So you can really think about, for instance, silicon nitride membranes with actual payloads, and essentially trying to input power. You can kind of imagine something like a rocket, like a strapped rocket firing off, and essentially trying to see what the dynamics look like in this range before we really start to launch things. But of course, when the picture is a little more clear and detailed, I think we're going to see a lot of very interesting dynamics that we did not expect, as opposed to the nice clean picture. And so in this early stage, I think in coordination with what we're optimizing for in Rails, the idea is to really be able to try to levitate objects that are maybe 100,000 times larger than anything that's been levitated with coherent light till today. So we're really quite excited about bringing together all of this different expertise to really look at new types of science. And so essentially what I want to end with here is to say that, we think this high-powered laser combination of high-powered lasers and these extreme aspect ratio photonic structures are going to really give rise to new types of nonlinear mechanics. In terms of the novel types of nanotechnology with extreme aspect ratios, we think there is going to be a lot of really neat physics that comes out of this. And if we look at really this limits of acceleration distance, we're quite excited to look at this, because we think that at the end of the day, we're going to come up with new designs when we have these new constraints, both the small scale and the large scale. So it's really going to push the neural network optimization to its limit, I think. And so, yeah, and I think one of the main things that we're really also looking at is the cost. So we're not just thinking about how fast we can make these things, but also how economically we can make each of these sails, because it's really a weird type of nanotechnology that's very powerful, but it's also very, in some ways, very costly. So that needs to come in there. And so, yeah, I want to thank everyone in the group who's been working on this. Also, Professor Miguel Bessa, who is now at Brown, but we're collaborating quite closely on this. And we really want to thank the Limitless Space Institute for all their support on our research. So thanks.
Hey, thank you, Richard. Appreciate it. Great presentation and overview. We got one more, and then we'll have some time for some questions from the panelists first, and then we'll be looking for questions in the Q&A window as well. So next up, we have Professor Remo Garantini from University of Bergamo, Italy. He'll be giving us a talk about traversable wormholes and warp drive, a road to interstellar exploration. Remo, you have the con. Feel free to share your chart deck and tell us your awesome plans.
Can you see it?
Yes, I can see your chart deck.
It's perfect. Oh, it's
yes,
okay. Okay, fine. First of all, I would like to thank LSI for this opportunity to present this proposal and this work that I would like to study in this in the next year. First of all, okay. First of all, I would like to present some of the proposals that we are going to we see on the literature, and as you can see, starting from here and going through to the improvement of technology, we have some kind of improvement even to cross the deep space, but with the usual problem that every kind of improvement, even in this very special part of propulsion, we have to we met a big problem that is a big problem dictated by the special relativity. Special relativity says that when you approach a speed that is close to the speed of light, you have a mass that continues to increase in value. So you need an infinite amount of energy to continue to have acceleration, and the problem is that you cannot break your barrier of the speed of light. So the speed of light cannot be broken unless also because of the hypothetical particle named tachyons are not yet detected, and there is no reason to have tachyons from the experimental point of view until now, of course. Now, proposal can be obtained by a traversable wormhole. Traversable wormhole is a prediction of the Einstein field equation, if you want. If you solve the Einstein field equation, you can find some particular solution that can give you some very special properties. This property is the create a shortcut between far distances into our universe. And so if you want to cross big distances, what you need is exactly a traversable wormhole, with a big problem. Once again, the problem is that you need something very special termed the negative energy. And this negative energy is concentrated on a particular region of this wormhole that is known as the throat. There is a very well-known wormhole that is it is the Schwarzschild wormhole that unfortunately has not this property of cutting the space and time in a way that you can cross it, because it is highly unstable, and so there is no possibility at all to use it like as a tool to cross far distances in space. So the first part that we need to solve is the set of the Einstein field equation. The Einstein field equation in an orthonormal frame are described by energy density connected to the form of the space, the so-called shape function, and the redshift function. It is responsible, for example, of the presence of a horizon in a black hole. This redshift function is connected to the pressure, so there is a balance between the pressure and the energy density to obtain something that is traversable. Note that this pressure, radial pressure, is also known as the minus the tension of the gravitational field. And finally, there is another equation that is connected to the first two. That is an equation of the conservation of the energy. So these three equations in a static solution, in a static framework, I mean spherically symmetric, are the necessary ingredients to find potential solutions. The cornerstone of this approach is the traversable wormhole metric introduced by Morris and Thorne, and this metric is defined in 4 dimensions. There is the shape function here and the redshift function here. This is a form that mimics exactly the Schwarzschild solution. Indeed, if you fix B of R as a constant, you can find that this can be set equally to the Schwarzschild mass, for example. There are some possibility to change the coordinates and passing from the so-called proper length to the Schwarzschild coordinate in this way, with the appropriate asymptotic limits, with the very important condition that there is a boundary condition here. You need a solution at the throat. Then, if you use this kind of setup, you can build, for example, some kind of matrix. One of these, as a simple example, is a very special traversable wormhole that has a big problem. For example, a problem is dictated by this calculation. If you try to estimate and the amount of the average null energy from the throat to infinity, this integral diverges. The meaning is that you cannot fix the amount of exotic energy, so the negative energy that you need to have a stable wormhole. Another example is the once again introduced by Morris and Thorpe, but it is also known as the Brunnikov-Ellis wormhole. In Schwarzschild coordinates as this representation, while in the proper length representation as a representation that is very close to the Minkowski space in spherical symmetry, with the introduction of a minimal length that is represented by the location of the throat here. And as a throat condition, you need a minimum at the throat, so it is the minimum point that you can reach, and you, in this way, can avoid to go into the singularity. And this condition is also related to the this other one condition. This is the flare-out condition. Well, some features of this wormhole are that it is known as a zero mass. The total energy is dependent also on the proper mass, that is changes the sign depending on the universe that you are looking at. And the radial pressure and the transverse pressure are represented by these quantities. In all, in these two examples, to obtain a stable wormhole, you need something that is called the exotic energy, something that is negative, and especially this kind of energy must be concentrated in a very small region, and this inequality must be satisfied at least in this region. And this property is equivalent to this other one, and this is the flare-out condition that I introduced before. One good candidate is the Casimir energy. Why? The Casimir energy, it is the only one source that can give something similar to the exotic energy, because when you estimate the 0-point fluctuation outside of this boundary represented by the plates of this Casimir device, and inside, you can find that there is a difference in the 0-point calculation, and this difference is estimated to be to assume this this value, where A is the separation of the plates, and as you can see, is negative. But what is important is that you are making a difference between positive energies, and the difference is negative, and this negative energy is inside the plates, not outside. It is only inside. And for example, for a surface of the plates of 1 centimeter square and the separation of 1 micrometer, you obtain a force that is 10 to the minus 7 Newton. The technology that we have is can reach the nanoscale, for example. So the force is just a little bit bigger. But what is important is that if we try to take seriously this Casimir effect, indeed we can have a solution, but this is the problem that this is not asymptotically flat, because when R is very large, this becomes negative, and this and having a shape function that is negative is not a good feature of a traversable wormhole. So in a sense, we need to cut off the region when B of R is becomes negative. So in the point when this is vanishes. Well, the idea is take the stress energy tensor, so the source of the Einstein field equations, replace this stress energy tensor from a classical to a semi-classical. So you introduce some quantized field, for example, scalar field, electromagnetic field, and other fields that can be quantized and have finite results with the help of some renormalization technique. What you obtain is a very interesting thing, and this is obtained when you promote this this separation that in the original Casimir calculation is fixed to a variable coordinate. So this can be integrated, and this integration allows to obtain a shape function that has the right features, and for example, for omega equal to 3, you obtain a new kind of wormhole, if you want, and this is the Casimir wormhole. And I draw to your attention that the omega equals 3 is respected, and this is the relationship between the radial pressure and the energy density. This is also the relationship between the energy density and the pressure in the original calculation in a flat space. This extra contribution coming from the transverse part is an effect of the curvature, if you want. There are some features you can calculate, for example, the proper length, and not only, also the differences between the time and the proper time. But in this case, it is not very different one each other. Well, there are other proposals that try to confine the energy density in a very small region. One of these is the generalized absurdly benign traversable wormhole. One form of the shape function is this one, is inspired. It is inspired from the original Casimir source with a constant energy density and non-variable, and you can find that there is a solution, and this solution close to the throat, it is similar to the original absurdly benign traversable wormhole that has this form. And this is very interesting because outside of this region here, the space-time is flat, completely flat. So the curvature is very concentrated in a very small region. Unfortunately, to have a wormhole throat that has a reasonable and physical dimension, you need a plate separation of picometer, but actually the actual technology allows to have a nanometer separation, so you have a very huge throat that is not real, is not physical. Another proposal comes from another idea of modifying the energy density close to the throat, and trying to put a Yukawa form. The Yukawa is a modification of the potential in such a way that this dies very, very rapidly. It is damped very rapidly when you increases the length from the source. And what is interesting is that once again, the prediction gives you a plate separation of a picometer, and even in this case, you can see that this is a zero mass wormhole, and the connection between this proposal and the Ellis-Brownnikov is the limit of this mu going to 0, and you can obtain something that it is very close to the very famous very famous wormhole that is the Ellis-Brownnikov. Well,
Hey, Primo, this is Sonny. You have 3 minutes.
yeah, okay, fine. Now, the idea for this grant is try to combine different sources. For example, try to probe an electrovacuum source of Casimir and electromagnetic. What you need, what you obtain is that the sum of their energy density and radial pressure is still negative. And what you obtain is that this kind of source assumes this form with the two lengths that come into play. The total energy density is still negative when R1 is greater than R2. And it is interesting that, for example, there is also a ratio from the radial part to the energy density part. And what is interesting also is that the fine structure constant comes into play. And the partial result is that the wormhole throat can be fine-tuned. And the fine-tuning comes from exactly from the charge of the electromagnetic field that is, even if produces a positive energy density, this does not affect the wormhole throat. It can be adapted to some to different lengths, from the Planckian to something that is larger. But larger, not huge. And this is very, very interesting. And of course, the idea is then to move from here, from the original electromagnetic source to a metamaterial that has the possibility of having a permittivity that is negative. And so this can be a mimicker from a potential exotic matter that can give you other solution. Unfortunately, there is a problem. The problem is that this kind of solution has the pressure and energy density ratio that is equal to -1. This is known. This is well known as the phantom divide. It is a very dangerous region, and this region is also represented by the cosmological constant, but this can be investigated. Well, our team will be composed by myself, Piero Nicolini, that is the previous research fellow of the previous LSI grant, a postdoc that has been introduced thanks once again to the LSI research fellow of the. So we had the opportunity to enlarge the group, and the new addition that we are going to that will be with us, I hope, in January. And the idea is that to study the effect of metamaterials combined with Casimir energy and the consequences on warp drive. Why this? Because the warp drive and the wormhole can be connected with a special transformation, and this is due to also has been presented 10 years ago, more or less, in a preprint by Homer Ellis, where he tries to connect exactly the drain hole with the Alcubierre metric of the warp drive. So this program can be realizable. we can do calculations and we can do estimates in this very limited amount of time. So this is our proposal. And for this opportunity, I would like very, very much the LSI for this grant. Thank you for your attention.
Thank you, Remo. As always, it's very interesting to hear all the deep background and all the different reference papers, and thank you for all the previous the three grant proposers that presented. This has been very educational. I hope the folks that are online watching enjoyed it. So we've got just a few minutes for questions here before we take a 20-minute break before we get into the afternoon session. So Remo, if you could stop sharing your slides, that way we should be able to see everybody.
Okay.
All righty, very good. So folks that are on the panelists, if you'll type questions, we'll try and lift those up as we get those. Let's see, we've got Kirill, you have a question, and this could go to any one of the previous four. You're not, we can't hear you.
Can you hear me now?
Yeah, we got you now.
Yeah, so I was so you're expecting that with this technology one could realize a traversable wormhole in the lab with the use of metamaterials and Casimir energy.
This is the question.
Yes.
Okay. No, the OP is the to estimate the possibility of having a source that is not trivial. And suppose we are able to modelize the metamaterial in such a way there is a spherical symmetry. Suppose we can do calculation, and we can do it. Which kind of wormhole we can have? It is bigger, it is smaller, it is I do not know. We needed to do estimation for this, and we need to try to put together all the physical sources that we have at in this moment in our time. I mean, because usually people, when you see the literature about traversable wormhole, everybody invokes the Casimir effect, but nobody says more about this Casimir effect and the connection with the traversable wormhole. So people speak about phantom energy, but you cannot manage a phantom energy in the laboratory. You cannot you cannot do anything. We need we only the only source that we have is the Casimir effect and everything that is related to the Casimir effect, nothing more. So this is it is the starting point of this research. So the metamaterial could be a possibility to mimic another kind of negative energy, a negative energy density, sorry.
Thank you, Remo. Very good answer. What other kind of questions do we have from the panelists? Adam.
Hi there. So a quick question for Richard. I really enjoyed your talk, and this is just a kind of like a technical question on the photonic crystals. How are they actually made? I'm just very curious how those holes are drilled with such precision so small.
Yeah, no, it's a good question. So I mean, so right now what we do is we essentially deposit a film, which is the sail material, onto a silicon wafer. We punch holes into it. So we just use an electron beam lithography right now to try to get this. But to make these really large scale structures, so for instance, the one that I just showed on this thing, this 4 centimeter by 4 centimeter sail, essentially took about 3 days of electron beam lithography to write. So you're thinking on the order of about tens of thousands of euros just to write the structure. So that's why we've been actually going a lot after the optimization of the costs of it, by, for instance, seeing how big of a feature can you make so that you don't have to do electron beam lithography, or maybe a much cheaper form of lithography that'll allow you to do this in a really large scale.
Great, thanks.
Yeah.
Thank you, Adam. Jeremy.
Great, thanks. I just wanted to thank everybody for great presentations. I enjoyed all of them. I'd like to ask everybody questions. I guess we're limited on time, so maybe I'll just start off with one for Andreas. I was wondering, with these graphene materials, very interesting materials, I wasn't aware of them. I was wondering, what do you know about their optical properties, and how was that included in the modeling? For example, they look like they're pretty black, so I'd assume they're kind of absorptive and maybe scattering. And you mentioned going to very thin layers, and I was wondering if they start becoming transparent on the order of 10 microns or so, or what your comments are on those materials.
Yeah. Great question. So aerographene, so the bulk aerographene, which has been manufactured, it's basically absorbing. So there's no reflectance, basically a black material. The question at which thickness it would become transparent, yeah, this is relevant. If you go down to 1 micrometers, then you go to the level of the microstructure of these tetrapods, and one possibility would be to manufacture these tetrapods at a small scale. And there's actually one paper which was published in, I think, Nature Letters, where a model has been developed for these tiny tetrapods, which can be scaled down. So if it could be scaled down significantly to a significantly smaller size than the ones which have been manufactured now, I can imagine that some kind of intransparency could be achieved. But still, if you think about, for instance, graphene sails, like monolayer graphene, it's basically transparent. So the same thing could happen with aerographene, yeah.
I see. And so for the calculations of kind of the velocities and times and distances and things like that, was that assuming then basically reflectivity of 0 then?
Yeah. Okay. You're specifically asking about whether in the Heller et al. Paper that has been taken into account. No, it hasn't been taken into account at all. Yeah.
Okay. So they just assumed reflectivity of 1 in that calculation?
So what they are assuming is basically an absorbing material.
Okay. Yeah. Yeah. Thanks.
Charles, I think you have your hand up.
Yes, thank you. I had a question for Richard. I found those the mechanical frequency combs that you discovered really fascinating. And I was wondering if you have thought about potential applications and how you would take advantage of that phenomena you discovered.
Yeah, no, so thanks, by the way. Yeah, so it was actually a really nice kind of discovery that came from the phase 1 that we weren't expecting. And it ended up being that what's very interesting about it is that acoustic frequency combs, these mechanical frequency combs, they have a very different use case than optical ones. You can use them for different types of metrology and kind of more opaque materials, say for seawater, these kind of things. But you can also start to think about using them in quantum applications where you need, for instance, like phononic circuits, and you really need some kind of frequency comb generation. One thing that I find that it's very interesting about it is that we essentially just use one laser to both drive the motion of this membrane and also to form the optical potential with which it moves. So the beam actually has a dual purpose without any like feedback control or any kind of precision tuning of the frequency of the light or modulation of the light. We just basically put in a beam. It both drives the membrane and also makes the potential so that it kind of moves through. And this is what causes the frequency comb. And I think what makes that interesting is that it makes it very very reasonable that you could actually miniaturize this very easily in a way that's not very difficult. So for instance, you just need one laser input. You don't need a lot of complicated optics to modulate it or anything. So that's what makes it kind of easier from the nanophotonic perspective if you want to put it on a chip You just need a laser, you just need and it will both drive and make the potential. So
Yeah.
you could think about miniaturizing it and making kind of on-chip of mechanical frequency combs, and in a way that's really much easier than other frequency combs.
Yeah, very interesting. Yeah. I think
Thanks.
Making some sort of mechanical circuit would be very interesting.
Yeah.
In some of the work we're doing now, we're looking at some non-reciprocal mechanical structures for controlling the vibrations, actually, and managing vibrations in spacecraft.
Yeah, well, I think it's funny because a lot of this stuff goes circularly, right? Like I got interested in this light sail business because I had been in optomechanics. I studied sales for a while, and I come back to finding out new things about optomechanics. So it's this, I think all of these subjects are somehow nicely related.
Yes.
Which I think makes it quite special.
Yeah, great. Thank you. Really nice work.
Yeah, thanks.
Thank you. Thank you, Charles. Good question. Looking at the clock here, it is 12:10. We're scheduled to take a break at 12:10 for 20 minutes, but right before we take the break, I do want to go back and highlight, Richard, you said something during your presentation. I just want to lift back up again. Kind of speaks to some things we've been thinking about here at Limitless Space Institute, right? You know, we're all motivated by these noble views of what we hope to maybe achieve, or at least make some progress towards, to enable us to get further out in the solar system and maybe start to reach the stars. And, you know, in my mind, the whole principle of pursuing a better tomorrow in space invariably, you know, helps us provide for a better today here on Earth. Because all this stuff that we're kind of trying to run down is going to have all kinds of off ramps, right, in terms of the technologies. And so I think that's the intangible and unpredictable aspect of basic research. So anyway, just you know, we've been thinking about that as well. And it's nice to continue to hear these success stories, if you will. We were pursuing this, and we found this and this and this, which is really cool. So just for when we come back, we will go over the 5 talks for the afternoon, and then we'll have another Q&A at the end, and maybe we can let that run just a little longer if we need to. But thank you so much for all the presentations this morning. And I'm going to go ahead and put us on stop video and mute, but I'm going to go ahead and share a screen that says we're on break, and we'll be back. So folks that are joining us on YouTube or on the webinar can at least see that we're still here, but we'll be back shortly. So I'll be bringing the loops back up at 12:30-ish, so we can get started with the afternoon session. So, all right. Thank you, everybody. See you guys in just a few minutes. Hey, Jeremy.
Hey, Sonny, how's it going?
Oh, not too bad, not too bad.
Good.
So everybody else back in front of their keyboards? Hey, Richard.
Hello.
Hi, Sunny. It's James. I'm subbing in again for Pete, or at least taking back my position from Pete.
Yeah, James, glad you were able to join us. Sorry to hear about your travel travails getting to London.
Don't worry. I'm in a taxi now. There's also a train strike in London, so it's all kind of a mess. But Pete told me I touched base with him, and he was very excited about the lights out presentations that he saw in the first half.
Yeah, I was going to say we definitely had some presentations that make us think, and then I know we have some more to continue to stretch our brains in the right kind of way. So I'm looking forward to a good afternoon discussion. So we have 5 in the afternoon discussion. We've got, and then after that, we'll have some Q&A, 20 some odd minutes at the tail end. Maybe we can go back and catch any I forgots or anything like that. I believe Chatura Vandatuga will be joining us, but he'll be joining us pretty close to his presentation time. He's in Australia, and so his presentation time of 1:50 Central Standard Time is, I think, like 5 some odd o'clock in the morning for him. So he might be a little sleepy eyed when he joins us. So, and I think we've got a lot of good discussions this afternoon. I think I was looking for Phil Lubin, see if Phil had joined. I haven't seen him yet. I know he's up right after Jeremy. But I tell you what, let's go ahead and get started. And if we get to the next slot and we haven't been able to get Phil with us, we'll jump forward to Adam, and then we'll loop back to Phil towards the end. So Jeremy, you have the con. Looking forward to hear your presentation on the Casimir torque thruster. Jeremy Mundy from University of California, Davis.
All right, great, thank you. So I assume you can see my screen okay?
Yes, we got it good. Yes.
Okay, perfect. All right, thank you. Yeah, so the Casimir effect has come up a couple of times in the morning discussion. So I'll talk about kind of a different aspect of the Casimir effect, and it's going to kind of put together a few different things together to arrive at this idea of a Casimir torque thruster. First thing, I'll give a little bit more background on the Casimir effect. Like I said, it was mentioned earlier by Charles and by Remo. And then I'll talk about this concept of a Casimir torque. So the idea that you can get rotations out of quantum fluctuations. And then also this idea of a dynamic Casimir effect where motion can give rise to the generation of real photons that are kind of promoted up from the quantum fluctuations. And by combining all 3 of these together, we'll propose a concept of a Casimir torque thruster, which is what we're aiming to further explore in this program. So first, since this is the Limitless Space Institute, we're thinking about space all the time. We oftentimes think about, stars and galaxies that are out there. But, what about all the stuff that's in between it? Well, it's mostly empty space, right? So if you're in the interstellar media, you have maybe 1 hydrogen atom in maybe a cubic centimeter or something like that. But it's mostly just empty space. But as we've also heard a little bit about, quantum mechanics says differently about that. It's not completely empty. And so we can arrive at these quantum fluctuations by thinking about electromagnetism. And so this is kind of a 1-slide overview of how you can get to quantum fluctuations. I think it's kind of a nice compact way of thinking about it. So just classically, we can think about Maxwell's equations, and this describes the propagation of electromagnetic waves. And so we know that the solutions to those are simple harmonic oscillators. And so we see photons, which are basically sines or cosines that are zipping around in free space. And this is all very classical. Now, if we want to treat the electromagnetic fields quantum mechanically, then we have to quantize those fields. And so this comes down to a simple problem of taking a harmonic oscillator, which are the solutions to the electromagnetic waves, and quantizing that. And so when you quantize a simple harmonic oscillator, you end up getting these sorts of solutions. And so you have that the energy eigensolutions are these h-bar omegas. So omega is the energy associated with it. And then you have some sort of 1 plus a half here. And so the 1 is usually some sort of number state. It could be different levels, or in this case of photons, it's the number of photons. And so this is what happens when you quantize the electromagnetic fields. And if you're in free space, you don't have any photons. So this 1 here goes to 0. But what you're left with is this 1/2 h bar omega. And this is the 0-point energy that was discussed earlier, which arises from quantum fluctuations. And you'll notice that because there's an omega here, basically you could have any frequency of photon that you want. And so if you add up all of this, there's a huge energy associated with this, and the energy density in fact, is formally infinite, but there's usually ways to introduce some sort of cutoff at the Planck scale or some other way in which you make this finite. And as was mentioned earlier as well, that there's also this kind of discrepancy between what you have in terms of the 0-point energy and trying to relate it to a cosmological constant, and that these things don't really add up. In fact, they're off by 120 orders of magnitude. So there's still some open questions about what's happening with quantum fluctuations and vacuum energy. So the first of the 3 things that I mentioned was the Casimir effect. And so the way that he was thinking about this back in the late 1940s was saying, well, let me make a cavity here. So I'll use some metals and see what kind of vacuum fluctuations can fit inside that cavity. And so you can add up all these different modes and you'll get some energy associated with that. You can reduce the size of the cavity and add up the modes there. And you'll see that there are fewer modes because you can't fit all of the long wavelength ones. So there's basically less energy in this smaller cavity than there is in this larger cavity. And so what he did was we looked at the basically potential energy associated with the system in terms of the number of modes that exist here in the quantum fluctuations. And so you end up with an energy between these 2 plates here that is given by fundamental constants if you have kind of ideal metal plates. So you've got that's related to something quantum. You have your h bar here. You know that light is involved. We have C here. And then we've got 2 parameters that are related to the external parts of the system, meaning the size of the plates, L squared, would be the surface area, and the distance between them, which is d cubed. And so if you have a potential energy that varies with position, you can take a partial derivative of that and you can relate that to a force. And so it turns out that based on these quantum fluctuations that gave rise to this energy, there's actually an attractive force here between these 2 objects that scales with some fundamental constants, 1 over the distance of the 4th power, and also with the area. And so this is a pretty interesting phenomenon because we started with kind of the nothing of vacuum. We saw that there's actually quantum fluctuations, and these quantum fluctuations can give rise to a somewhat macroscopic force between objects. And so there exists an attractive force between these plates in vacuum due to purely the quantum fluctuations. And so this prediction was back in the 1940s. Since then, there have been a number of experimental verifications of the Casimir effect. And so about a decade after his original prediction, there were some early experiments looking at kind of advancements in force measurement techniques, and then also ways to try to modify the Casimir effect, either looking at ways you can modify the dielectric response or the geometry. And so a few things that we've been working on in my lab in terms of experimental measurements of the Casimir force. We looked at a number of years back at metals and fluids. So we can talk about Casimir force in vacuum. It turns out that you still have this even if you're in fluidic environments. In fact, in fluidic environments, you can make it so that the quantum fluctuations will give rise to repulsive forces. We've also more recently been looking at geometries and how you can change the curvature to change the force. And also looking at the effect of optically anisotropic materials. And that actually brings me to the next point that I wanted to mention, which is what happens to quantum fluctuations when the materials are not isotropic. So for example, rather than having a metal plate that it doesn't really matter how you orient it, the optical property is the same. If you had something like a polarizer or a birefringent crystal, where now depending on the orientation, the quantum fluctuations see different boundary conditions. And so that's the next question is what happens when you have these optically anisotropic materials? And so it turns out if you could imagine taking 2 polarizers or 2 birefringent crystals like calcite and you line them up and you've got some sets of fluctuations that can exist between them, if you were to rotate them a little bit, you've now changed the boundary conditions on those electromagnetic fluctuations and you've changed which ones could fit inside here. And so what that means is that the energy now associated with that depends on the angle. And so if rather than just being concerned about the distance dependence, we now have an angular dependence of that energy. So you can take a derivative with respect to the energy, and you'll see that there's a torque associated with that. So this was first predicted in the 70s. So there's some work in the early 70s and also the late 70s independently they kind of came to this conclusion that there should be some sort of rotation based on optically anisotropic materials being put close together inside a vacuum. And so a few years ago, we set out to measure this. And so what we did is we looked at an optically anisotropic material that was solid. So this would be a birefringent crystal, and then also a liquid crystal, which is also optically anisotropic, but now is also a type of fluid so that we can more easily maneuver it. You can basically put this into an optical microscope using some cross polarizers to look at the rotation of the polarization due to the turning of this top birefringent material as a result of quantum fluctuations between it and the bottom one. And you can see macroscopically, so these are 1 centimeter by 1 centimeter discs that have been prepared in such a way that there would be a Casimir torque between these objects. And so depending on how far apart they are, this is looking at kind of different separations. You'll see different color changes here. So when they're light colors, it's strong torque, and dark colors is weaker torque. So you can kind of see that the magnitude of the torque changes as you change the separation. And this is kind of an interesting picture here, again, 1 centimeter by 1 centimeter, where we've taken this top liquid crystal and we've rotated it and put that in close proximity to another birefringent crystal. And you get this sort of fourfold symmetric dark light pattern here. And it looks pretty symmetric here, but it turns out that the Casimir torque will kind of change the orientation of this ever so slightly. And you can analyze that in order to determine the angular dependence of the torque. And so I'm not going to go through all the details of this sort of thing here, but we can look at different types of crystals, and we see there's kind of a sine to theta dependence of this torque. So basically that the quantum fluctuations are causing one optical axis to align with another one. And we can also look at kind of the distance dependence of that. So this is the idea of the anisotropic boundary conditions giving rise to a torque. And so then the final of the three concepts that I wanted to bring up was this idea of a dynamic Casimir effect. And so for the dynamic Casimir effect, I like this cartoon that I found. And basically this is the concept. So imagine you take a box, okay? You've got nothing in the box. You close the box, and then you shake up the box. All right, so then you wonder, well, what happens when I open this box? Well, if it's a normal box and you have a normal classical vacuum, you open it up and you still see nothing inside. But with quantum mechanics, it turns out that what happens is you then have a box full of photons. And so this is related to basically moving boundary conditions. And if you can oscillate this box at a high enough rate, you can generate photons. And so this concept was also brought up kind of in the 1970s. And there have been a number of works since then. But the basic idea is that if you have a mirror, some sort of mirror that gives a boundary for the electromagnetic fluctuations, if you can start to oscillate that mirror, you can kind of promote the vacuum fluctuations into real photons. So there's a nice kind of somewhat simple expression here where you can relate it to the kind of oscillation frequency, how long you're oscillating it, and this is kind of a ratio of the velocity of the plate to the speed of light. So you can get an idea of how that works. So this has also been experimentally verified, also only in the last 10 years or so. And it's been done with a couple of experiments. So the first one here is looking at a superconducting quantum interference device, a SQUID, where they're basically, rather than taking a mechanical mirror and shaking it, what they've done is they have a material where they can change the electromagnetic boundary conditions rapidly. And so you can imagine if you have something where you can take effectively a mirror where it's changing the index of refraction, for example, or the conductivity very rapidly, you could generate an effective mirror, which allows for a kind of megahertz scale generation of photons. There's another recent example looking at basically a fiber, an optical fiber, where you can cause undulations of the material as well. So you're, again, effectively changing that boundary condition for photons that are coming through, and look at the generation that way as well. So that brings us to the idea of a Casimir torque thruster. And so the concept is as follows. Imagine you take an optically anisotropic material. So again, this could be it could be a birefringent disc of calcite or quartz or something like that, or it could even be a metallic grating, but just something where the optical properties depend on the polarization. And so suppose you take that object and then you start to rotate it. So now we have electromagnetic boundary conditions that are rotating, so they're changing at some particular rate. And in principle, you could use this to generate photons, which then could be used for propulsion. And so you could do a simple kind of, so this is the idea of a Casimir torque thruster. You could do a back of the envelope calculation if you want. And so if you were to imagine that this works kind of like the oscillating mirror, so that sort of expression goes as the frequency of oscillation, and this is that beta squared terms of velocity of the object over the speed of light. And for our rotating disk, we could say, well, let's suppose that rotation disk, the rate at which it's rotating is related to the rotational speed, and we know it's a disk of a certain size. So then we can come up with a photon generation rate that would look something like this. So it would scale as kind of the radius and the radius squared and the frequency of oscillation to the third power. And so again, you can kind of plug in some numbers for this. So imagine you have a kind of micro scale disk of 20 microns, gigahertz rotational speed, which is kind of at the limit of technology, but reasonable. And you'll generate about 40,000 photons after about 24 hours. And so this is for a very small disk. You can imagine having a meter square of these little disks, and that would give you something on the order of kind of 10 to the 9 photons per second. And so there's lots of different ways to scale. And this is, again, kind of very back of the envelope calculation, but that's the concept that we're looking at. And so that's what we're proposing to look at with this LSI seedling grant. And so here's kind of our time scale of what we're planning to do. This year, we're going to, the first kind of 6 to 9 months, we'll be looking at kind of evolving these simple analytical models and trying to come up with some kind of more exact ways of thinking about it, taking into account the fact that these are actual disks and anisotropic materials with rotating boundary conditions rather than just oscillating mirrors. And then in the last portion of the program, we're going to look at the feasibility of trying to do something like this experimentally and what that would take, as well as how this might be scaled up to an eventual technology. And here's a couple of kind of cartoons. I had mentioned this kind of disk of an anisotropic material. You could also think of some sort of propeller blades sort of system. So there's a lot of different sorts of geometries, either just some way that you want to modify the optical properties, whether it's through geometry or through the birefringence of the material. And so with that, I will go ahead and wrap up here. I have a question slide, but I think we're just holding the questions till later on. So I'll just pause there.
Hey, thank you, Jeremy, for a really good overview, brief and concise. Really appreciate that. I have to say, I love the back of the envelope calc, man. That was fantastic. That was good stuff. So
glad you enjoyed.
So I see we have Phil with us. Phil, we're going to put questions to, we have a 20-minute bank of questions at the end of the 5 presentations for the afternoon session. So just remember which question you were going to ask, and we'll definitely come back to that. So next up, we have Phil Lubin from UC Santa Barbara. Let's see, the title of Phil's talk is The Path Forward Directed Energy Phased Array Technology. So this is some beamed energy propulsion, solar sail stuff. Phil's back with us again this year. So Phil, I'm going to hand the microphone over to you, and you have the con, and I'll just chime in and give you a 3-minute warning when we get there.
Okay. Can you see a screen that now goes to full screen?
I can see the PowerPoint, and now I see it full screen.
Okay, very good. All right. So, all right. So I'm going to give you a quick overview of our program, which is decidedly on a very much operational phase in the sense that we're building hardware. So I want to just give you an overview of what we're doing and where we're going and why we believe it makes complete sense in the larger picture of trying to achieve really transformational things that one can do in space that you can't do currently. So let's see. So our technical plan was to, as proposed, was to go towards a meter scale array, which I'll explain what that is in a bit. We were asked to descope a bit, so we descoped some of the outdoor tests. We're also looking at an operational phase where we put something on the moon that allows us to beam power and acts as a phase locking portion of the program. We just scoped that a little bit as part of the descope. We're also looking at phasing over extremely large number of elements, which will be clear in a bit as to why that's important. And we're using some techniques involving spatial light modulators to do that, in addition to our phased array. We're also building, you'll see an example of an absolutely stable, absolute phase stabilized link, and that will be clear in a bit. And then we're doing some work on technical and economic drivers. Not only is this a technologically driven program, but you'll see that we've come a long way. And now the question is, so how do we go to the implementation phase of building something which could help us achieve relativistic flight? And part of that is going to come down to economic drivers. So here's an example of something that where we're reducing the cost of a critical part of our system by about a factor of 1,000 by using some innovative optical techniques. Okay, so there's a lot of things here. I'm not going to try not to bore you on it, but we're quite productive in papers. We've produced now over 60 papers on our directed energy program. We have 2 books out. These are the papers in the last about year and a half. Most of them are fairly technical, and you can find them on our website. Just Google us and you'll find it. But anyway, a number of these are directly a consequence of LSI support. So why directed energy? Directed energy provides, I would say, one of 2 sort of current physics-based approaches, and I don't mean that other things aren't possible, but in terms of things that we currently have on the table, one is using matter-antimatter annihilation engines if you want to achieve highly relativistic flight, and the other is to use light itself as sort of a propellant, if you will, and we're operating on the directed energy side of that. So it's a path not only to relativistic flight for interstellar capability, but it's also a path for very high-speed missions within our solar system. The same infrastructure, the same core technology that we're developing can be used for operation within our solar system to not only transfer power from point to point, but to enable very high-speed missions. And I'll show you some examples of that in a bit. So this should be understood in a larger context, that you're developing a technology which has an extremely large number of uses. And this roadmap that we're developing has a number of off-ramps, as we call them, which are technological applications of that technology. Okay, so why directed energy propulsion? So if we look at that which we're currently using for propulsion, chemical, ion engines, possibility of using nuclear, solar cells, these unfortunately do not enable radical advances. Not that they aren't useful, they are. Not that we shouldn't pursue them, we should, but they do not enable the radical advances that you'll need to achieve relativistic flight. So large-scale directed energy is an example of something which enables breaking sort of what I call the status, not coup, status quo, sorry about that. And it's not only a roadmap to relativistic flight, but it's also a technology with a large number of uses. We've shown what I think is a rather incredible number of results. We've shown that we can phase lock out to 50-kilometer baselines, which, for example, is the equivalent of putting a 6-meter spot on Mars. So just imagine focusing a spot from Earth to Mars. And we build our own devices. So we've achieved 50% bidirectional amplification with enormous dynamic range. And we've demonstrated beacon locking on target at close to the photon limited regime. So, I mean, so far so good. And now a question becomes, so how do we deal with, there's a few technological, I would say, tall poles that we want to overcome, but there's also a lot of economic tall poles that you need to overcome. These are not fundamental limits, but they're very important in terms of realization, because if it's too expensive, then you can't afford to do it. Luckily, it's an exponential growth technology, so time is on your side. Okay, so I'll talk about some things from very small scale, such as with a meter, we can get to transferring power to LEO. 10 meters, we can transfer power to GEO. We can also send a small mission to Mars, faster than chemistry. And then it points the way towards relativistic flight, which requires of order kilometer class array. There's also the same technology will allow humans to get to Mars relatively quickly. About 30 days is one of the missions we studied for NASA. Not a flyby, but for humans who want to land. So that's an interesting approach. Okay, we have a roadmap, and the roadmap is from the laboratory scale, which we're at now, going into the outdoor testing phase. But it goes along both a sort of an operational point of view. You'd like to go Earth to LEO GEO, long range power projection, as we call it, to fast solar system missions, fast human transit, and then to outside the solar system. So these are capabilities. In terms of things that we're building, we're working on phased arrays, and you'll see examples of that, physical realization, and then the number of technologies to implement, including using the moon as a point of reference. Okay, what makes it possible is that, like a supercomputer, you can make very powerful things from a large number of less powerful things. So here we use a similar topology, where in order to make a very large source of light, in order to use those photons to propel you with, we take a number of smaller, in this case, optical amplifiers, and then gang them together in a parallel scheme and form a phased array. So in a sense, this is a parallelization problem. Power is actually not the problem. You just add more, but parallelization and phase convergence is the problem. And that's what we're working on, and show examples of where we are. Currently, what we've achieved and shown is that we can achieve a phase error. And those of you who might be familiar with optics, such as that which is on James Webb Space Telescope, or HST, know that you want to achieve a surface finish better than about 1/10 of a wavelength in order to get good STREL, or energy on target. Power on target. We've achieved better than 1/100th of a wave at 11-kilometer radius. And we've also done some tests out to 25 kilometers and achieved much better than 1/10 of a wave. So we've achieved much more than we need to achieve in terms of phase error. And this is using fibers. So we've achieved better than we need. And that's remarkable. I didn't think we'd do that so rapidly. The phased array system architecture basically starts with a narrowband, narrow line width source, something you can hold in your hands. And then we build a series of low noise amplifiers, which we've now achieved about 50% efficiency there. We're operating at 1064 nanometers. Then you need to go into a heavily mathematical regime of phase control algorithms and convergence, and how you'd handle the topology, and then the array architecture. And so we'll talk about this, show you some examples. Here's an example of one of our amplifiers. This one achieved 42% wall plug efficiency. You may have seen today, there's an announcement on laser fusion at Lawrence Livermore. For example, their efficiency is much less than 1%. We've achieved nearly, our bests are 47%. Here's a kind of an average one at 42%. And we've achieved greater than 30 kilometers coherence length. That's not distance to target. That's the spread of the array. This is greater than we need. In order to achieve interstellar flight with small payloads, you need about 1 to 10 kilometers of array size. We've achieved greater than that already in our amplifiers, and these are built in our lab. Okay. So our topology provides a complete phasing solution, namely that you can take out the perturbations from atmosphere, microphonics, system perturbations by locking to the target. It's what's called a cooperative target. You're not trying to blow it up as you are, say, in a directed energy weapon system. You're trying to actually reach out and send power to it. So it's a cooperative target. So we built in our laboratory on optical benches a lot of spaghetti, and doesn't, it's not beautiful, but I'll show you some more beautiful things in a moment. but we've achieved, and this is real, this is not just hypothetical. If you look back at our 2015 paper, and even back to 2013, we've outlined a path forward. Now we're starting to physically achieve that path. And so far it's working as we had hoped, actually better than we hoped. We've also added things to inject perturbations in the system. For example, atmospheric perturbations using a deformable mirror. And to some extent, this is like an adaptive optics problem on large telescopes, except here we have complete phase control over the sub-elements. So we've injected into our light path perturbations of all kinds and shown that within reason, we can take out those perturbations at an acceptable level to us. Okay, I won't, those of you that are not into photonics, I'm trying to bore you, but what is kind of interesting is that we have built this phased array test bed, and now we're beginning to sort of what it's called operationalize it, which you'll see in a moment. We've shown that we can phase lock to a few hundred picowatts per sub-element, and that we have an enormous dynamic range, greater than 37 bits, greater than 100 billion to 1 dynamic range in full bidirectional operation. We can simultaneously transmit and receive, not in time gating, but simultaneously with greater than 100 billion to 1 dynamic range, which is sufficient for achieving what we want to achieve. Again, for us, achieving means ultimately achieving relativistic flight, even though that'll be sometime in the future. NASA asked us to look at other applications of the technology, such as could we get people to Mars in a rapid timescale. They asked us to look at 45 days. We came up with about a 30-day possibility. This is not using direct momentum transfer, but this is using beam power to ion engines. Same architecture on the phased array side. On the spacecraft, what you do is you convert to electricity to drive an ion engine. So this is for high mass missions that are not going relativistic. This is for missions in our solar system, as say to Mars or to the outer planets. This is for, in the case of what we looked at and published last year in Sheeran et al. In 2021, we looked at missions up to 100 tons, delivering about 15 tons to Mars, for example. This one is transfer into Mars orbit. You don't have to have a laser ray on Mars to slow you down. You can do it all from Earth, or preferably from the moon. And in order to do that, you'd need arrays that are a diameter of order kilometer and power levels of order hundreds of megawatts, which is large, but not crazy large. The thing we looked at, which we thought was a great starting point, is to send a CubeSat to Mars. And that would take about 120 days for a small mission, about 10 kilograms wet, 4 kilograms delivered to Mars, flyby. You only need a 10-meter diameter array and about 1 megawatt of power, of which you actually only deliver about 600 watts to the spacecraft. So this is designed to be small, even though you use more power than you need to. If you want to make it larger, you use less power. So this is a good starting point because this is realizable. This doesn't have to take 20 decades, to get to. Okay, we're focusing on some economics as well as technological issues. Here's an example. We're building diffractive optical elements. This allows about 1,000 to 1 reduction in cost. And allows extremely high efficiency because we're narrow band, so we can tune it to our wavelength. Also, we're working with a commercial provider. It's a roll-to-roll process. You can literally roll these things out like a newspaper, and you can. This is not a joke. Their production rate is about 10 square kilometers per month. It's just an amazing number. So the cost to be to us be less than $1, probably about 10 cents. For one of these things, whereas currently we spend actually about $2,000 for the optic. Okay, so here's an example. This is hardware that we're currently putting together as part of the LSI program. This is a 7-element array. Each of these sub-elements is about the size of your hand and about the length of your arm. Here's hardware shown in the lab. Each sub-element, as we call it, consists of an optical element at the end, like this diffractive optic I just described, and then a full photonics and electronics subsection. So these are all identical, and they, in theory, can be mass produced. It's still not what you'd want for the relativistic case, where you'd want to reduce this to a sort of photonic integrated circuit and some other things, but this is a start. And these are sort of human scale. So here's a human, and here's a 1 meter array would be 4 of these put together. So modular construction, this is what we're building now. And you'll see a picture just like you did before of actual hardware. The sub-elements of all the photonics, all the amplifiers, all the electronics, all the phase control in one unit, ready to be mass produced. We're producing 7 of these for the program. Here's some of them laid out. You can see 5 of them laid out here. Here's one of the one of our staff members working on another optical table on this. Here's some temperature control, just looking at how we get heat out of the system. It's about 50% efficient, so you do have some heat rejection. Okay, so for a future application, one of the things we're particularly excited about is the possibility of using the moon. And this is an example of using a small spacecraft that would land on the moon and carry with it a phasing beacon. And we would then put spots on the moon using the small array that we're building for the LSI program. And this is a simulation of what you would see on the moon. And you would take a picture on the moon on the same spacecraft with a wide field, high sensitivity infrared camera, and you would see a spot pattern on the moon. So why do you see a bunch of spots rather than one nice spot? Because we would be using a sparse array on the Earth. Why? Because this is a realizable program. You could literally take the 7 elements we're building for the LSI program, array them on the Earth, separate them by of order 100 meters or so, and then you would produce spots on the moon. So it'd be kind of a neat example of the technology. Here's another example. One of the main things we build in our lab are sort of custom photonics. So this is one for the lunar beacon. So we're building this as a part of the LSI program. Okay, here's another thing that we built recently, which is an absolute phase stable link. And we're not sure if we're going to use it or not, but we literally put it together in about a week. And this is an example of how you can achieve very rapid progress when you build things yourself. So this is our own custom amplifiers, and we just put together the parts that we happen to have, optical modulators. And anyway, it works. We're figuring out if we're going to use it or not.
Hey,
Okay,
Phil, this Sunny, you got 3 minutes.
Yep. I'm have my timer. I show 1 minute, so I'm trying to proceed rapidly here.
Okay.
So this is the work in progress. On the photonics side, we're validating some of our hardware. We have a fiber tip actuator to allow us to do first order tip tilt correction for the atmosphere. So, to be honest, we'd rather not be on Earth to build this program. But we're on Earth now because it's way cheaper to be on Earth than to be where we'd like to be. We'd like to be on the moon. But for now, we have to be on the Earth for economic reasons and practical reasons. When you're on the Earth, you have the Earth's atmosphere to deal with. You have the perturbations in the atmosphere that you deal with. One of those perturbations is the first order tip tilt correction. And then the higher order corrections are done by phase corrections. So every sub-element has a tip tilt or first order corrector on it. So we've built those. Algorithms, we're exploring more sophisticated algorithms. Currently, we use a stochastic parallel gradient descent algorithm. We're looking at a variety of additional algorithms, including some neural network algorithms. The stochastic parallel gradient descent seems to work well enough, but we're looking at additional algorithms to see if we can do even better. We are integrating a fiber tip actuator into every sub-element. That's already being done. And then we're looking at ways of making these really cheap. So we've gone out and done some 3D printing of these, and those seem to work so far. One thing that's kind of a critical milestone we'd like to do is achieve 1 million element phasing. Now, we can't afford to build 1 million of those sub-elements I showed you. It's too expensive. So what we're doing is doing 1 million element phasing by a sort of a surrogate method. that's currently underway in a separate program. We may or may not use this. We can do absolute link stability. As I showed you, with the use of a acoustic optical modulator. This is an interesting way to proceed for some applications. Not clear that we'll need that in the long term. And then outdoor testing is one of the key areas that we would like to explore. We operate a high altitude test site for another one of our cosmology programs, where we have a 4-kilometer altitude test site that we'll use for the outdoor testing phase. And that, I think, is it. So I'm, I guess, under by just a little bit here. I'll stop there.
Awesome. Thank you, Phil, for a wonderful presentation, and congrats for not, like the last couple times we've done this, getting the green frog, right? Landon Zinski sitting here with me in the office. He's like, Sonny, I missed the green frog. You got to bring back the green frog, right? So for the folks that are new to the LSI grants, as part of my 3-minute warning, I just would replace the LSI picture with a green frog, right? So that was my way of letting people know that they were about to turn from a prince into a green frog. So anyway, thank you, Phil. Appreciate it. That was great. Thank you for joining us. I believe you had a question from earlier, so just keep that in your mind as we move into the next few presentations. We'll get to some Q&A. So next up, we have Dr. Adam Kay and Professor John Bush at Massachusetts Institute of Technology. And they will talk to us about some work on dynamic vacuum models of the electron. So Adam, John, you guys have the con, and I'm going to go to mute, and I'll give you the 3-minute warning when the time comes.
Great. Thank you so much, Sonny. Can you guys see my screen?
Yes, we got it.
Great. So yes, thank you to LSI for this opportunity. Appreciate it very much. Like Sonny mentioned, I'm working with John Bush in the mathematics department as a postdoc. And this coming year, I'm going to be pursuing a research project which is the other side of the stuff that Phil was talking about. He mentioned things that are on the table now, and what I'm trying to do is potentially expand the table. So this is my first slide. This is my son. He saw the educational and inspirational video that LSI produced, and it inspired him a lot. He basically did his first grade project on going incredibly fast. And those of you who have seen that video know that there were three different kind of space flight solutions, and the final one was something that would go 10 times the speed of light, and at these speeds it's capable of reaching Saturn in about 6.7 minutes and Proxima Centauri in 5.2 months. And as is very clear, as was made clear, this is unknown physics and unknown engineering. So taking this possibility seriously, it's obvious that we need a fundamental breakthrough of some kind, need to extend the table, as it were. And this is why I'm looking to try to make some incremental progress in this direction. But obviously this is a high bar to reach. So where should we look if we're trying to do this? And I think that a recent quote by Sabine Hassenfelder is a pretty good place to start. She said that in the past decades, physicists have not succeeded in solving any of the open problems and the foundations of their field. Indeed, it's not even clear we are sort of solving them. In this situation, it makes sense to go back and look for the path we did not take, the wrong turn we made early on that led into this seeming dead end. The turn we did not take is in resolving the shortcomings of quantum mechanics. So this seems reasonable considering the controversies that surround that. Very, very important theory. So connection, quantum phenomena. All hydrogen discovery that's about
Hey, Adam.
1570. You have a oil drop
Hey, Adam.
on a vast substrate of oil. Yeah.
Hey, Adam, this is Sonny. Could you turn off your video? That might help with the bandwidth.
Yeah, hold on. I'm going to try to also move because I didn't know that I would have problems with my bandwidth. Hold on. Here we go.
Sure thing.
Let's try this. Is this a little bit better?
Yeah, I think it's getting better. And if you want to, just for belts and suspenders, go ahead and turn off the video. It'll help with the bandwidth just to make sure.
Sure. Let me pull up Zoom and try that. Hold on.
Sure.
There we go. All right.
So we got you 5x5. You're good.
Great. So the idea here is you have a bouncing droplet on a substrate, and it can bounce indefinitely, and it can even interact with its wave field that it creates on the substrate and self-propel. And there are a wide variety of quantum analogies to quantum systems that have been discovered with these experiments now, ranging from tunneling, description of Landau levels, collections of these droplets can bounce in and out of phase and can mirror some aspects of macroscopic kind of like large scale material systems. And so let me show you one of the most inspiring ones of these analogies. And what's happening here is this is a droplet confined to a corral. It's in a high memory limit, so you have a very complicated wave field that's pushing the droplet around. At any one moment, it's very complex, but the path has been color-coded with the speed of the droplet. And a pattern begins to emerge out in the long time limit, which winds up generating a statistical probability distribution for the droplet. And as it turns out, this is basically identical to the probability distribution you get by solving the Schrodinger equation in a circular quantum corral. So that's very interesting. And it is, what's even more interesting is that it's reminiscent of the very first interpretation of quantum mechanics, which came about by de Broglie in around 1925, 1927. Around the time that he wrote his thesis, he was imagining matter, subatomic particles and things as actually an oscillating objects in some way. This has been called his clock hypothesis. And then he proposed what was called the double solution, where you have this oscillating piece of matter which interacts with a ambient wave field, which then determines its motion. And this picture has been recently revitalized by the work in hydrodynamic quantum analogs. So one of the limitations of HQA work for the last 15 years or so has been its restrictions to two spatial dimensions, where the wave kernel is a cylindrical Bessel function of the first kind, and it's basically a standing wave that decays in time. And with previous work supported by LSI, we examined the 3D system using numerics, and we modeled a spherical Bessel function. So one of the outcomes of that work was we uncovered some novel dynamics that are unique to 3 dimensions. And in particular, it's a helical spin state. So you see towards the top of this diagram, there's kind of like a chaotic path that's zipping around. This means that the wave field is very long-lived, and it's interacting with a lot of echoes of its past trajectory. And it then spontaneously stabilizes into a helical state, which then travels outwards, spinning around. So here is a cross-section of the actual wave field in this model, and you can see the droplet in 3D is describing a helical trajectory, basically in and out of the surface of the image. And so the thing that is quite interesting about that in this context is that it's reminiscent of a proposal of Hestini's in the 80s, where he was suggesting that we should think about the electron, and in particular the electron spin, as being like a localized helical motion. And he was talking about the Zitterbewegung, which was discovered by Schrödinger when he analyzed the Dirac equation. And he was, Estini suggested that we should try to rationalize spin as a physical process in which the electron goes around. So these connections are kind of what motivates the specific numerical study that I'm planning on doing, which is to introduce a analog magnetic field using the formal analogy between the Coriolis force and a magnetic field, of a charged particle in a magnetic field, which is given by the Lorentz force, to examine what happens when the two vorticities interact. So you'll have the helical vorticity as this droplet, the 3D droplet moves through space, and then you'll have the rotating ambient vorticity that's modeling magnetic field, and we'll see something, and I'm wondering if it'll be something similar to the Lorentz force of a charged particle in a magnetic field. So that will be very interesting to see, and that's it expresses the kind of fundamental intuition behind this research project, which is to try to find dynamical understanding of the electromagnetic forces. So that leads to the second part of this research proposal, which has to do with acoustic radiation forces. So these are forces that emerge when you have, say, a bubble or a particle that's suspended in an ambient fluid and then irradiated by a sound field. So these bubbles will change their volume, and then they'll experience a net directional motion that results in drift. So they do move in both directions with the sonification, but there's a drift that winds up generating a net motion, which you could interpret as a kind of force. And this is an example of these in action. So when it was still, the ultrasound was off, you turn it on, and that plate, which has bubbles on it, kind of goes over the substrate on the bottom that also has bubbles. So there's two different types of these forces. One is if you have a single bubble or particle and you sonify the fluid, it will move itself. That's called the primary force. And if you have two bubbles or more, then as they are sonified, they have volume fluctuations, which then set up an ambient wave field. And then those waves interact with each other, and then the two bubbles then wind up interacting. That's called the secondary force. And both of these are called Bjerknes forces. So these forces have a lot of applications in their areas, including acoustic levitation, biomedical ultrasonics. They're used in liquid degassing, even in food processing. And that's less than half of the types of things you can see in the literature. However, when you kind of scan the literature, you see that nobody ever really talks about the original research that Bjerknes did. In fact, there were two of them. So this rich literature kind of has forgotten the origin of the forces. So there were two of them. One of them was the father, Carl Anton, and then his son Wilhelm worked on it. And in fact, the secondary forces, or the forces between a pair of these volume oscillating bubbles, they were the primary concern. And the reason they looked at them was in order to generate a hydrodynamic analog to electrodynamics. So here's an example of what they actually did in one of their experiments. And it has like different parts. So there's a wire on the left that is turned by a motor. And as it turns, there's a piston that's marked P, and it basically just goes back and forth, and it hits the drum. And this drum produces then a pressure impulse, which travels down the pipe to the right. So this is the larger part of the experiment. You have these pipes going down, and they're attaching to two balls marked A and B, which are submerged in the fluid, which isn't actually shown here. And as the engine moves, it sets up these, basically a pulsation of the balls, which generates a volume pulsation inside. And the waveform that is generated in the fluid is actually basically a spherical Bessel function, which is the same waveform that we use to model the 3D hydrodynamic quantum analogs. And then the last thing to note is that the arrows on the left that show the direction of these pistons, they're out of phase. So this is the result. When these balls pulsate, they drift. This is the secondary Bjerknes force. And they actually, if you compute their motion as a force, it falls off as a square of the distance, just like the Coulomb force. And it also depends on phase. So when they are in phase, both contracting and expanding at the same time, this is in the upper figure, they attract. And when they're out of phase, they repel. So this is an old, this is from one of their books, and they labeled these phases N and S as an analogy to the north and south poles of a magnetic field. So the difference between the phases is interesting because when you have the same phase, you have likes attracting, whereas in physics they repel. So this has been called, and it's in, obviously the converse is true, opposites generally attract in physics, but here opposites repel. So this was called by the Bjerknes the inverse pole law, and it was not understood why it's different. So this is something that I think is very interesting. So both of Bjerknes, the father and the son, both of them pursued this analogy for several decades. And they showed that the hydrodynamic case is very close to the electrodynamic one in a very wide variety of domains. So this image shows the lines of oscillation in the fluid, and they are just compared to the magnetic field lines, which is something like the first scientific experiment that children do a lot of the time, where you just take iron filings and drop them on a piece of paper over a magnet. So the younger Bjerknes summarize the situation roughly like this. There is an extensive geometric analogy between hydrodynamic and electrostatic fields, which goes even into the most minute details. So this then leads to the motivation for the second part of my research, which is essentially a reanimation of the Bjerknes analysis. A lot of the stuff they did is very formal. They did a lot of mathematical work. And I'd like to basically translate this into a modern context. And this also includes connecting this work with the work on HQA, as well as De Broglie's clock hypothesis. And it's an interesting historical fact that De Broglie actually knew about the Bjerknes work. And when he proposed his own clock hypothesis for the oscillation of an electron, he said that this could have been anticipated because of the Bjerknes work. And then finally, I'll point out that there's also, we're also looking to potentially recreate some of their experiments in the lab at MIT. I think that'd be very fun to do. So kind of wrapping everything up here, try to like paint the picture. So we have a concept of particle oscillation, and it led De Broglie to his idea of matter waves, to the harmony of phases that he presented in his thesis. That led him to the double solution. And that is in turn extremely close to the analogy we have in the walking droplets of HQA. And then that's also connected to the particle oscillation of Bjerknes that he used to attain an electromagnetic analogy. So analogies are very useful. They've been very useful throughout history. They've always played an important role in physics and mathematics. And they suggest, basically what they do is they suggest unexpected routes. And I think that analogy, the fact that they've been successful in the past shows that it's a good way of placing research bets today when you're trying to do something like, as ambitious as a fundamental breakthrough, right? So people who are taking LSI's primary objective seriously, I think should be unapologetically bold in their ambitions. And we know that a leap forward in fundamental science will probably be a prerequisite to achieving the kind of travel times to Proxima Centauri where you could get there within a human lifetime. So, obviously such a leap forward will be hard, but is it impossible? That's an open question. And regarding that, I will leave the last word to Mark Twain. I think it's very brilliant. They didn't know it was impossible, so they did it. Thank you all very much for your attention.
And that's great. Thank you for that. Really good charts. Enjoyed going down some of the history there. It's good to see some of the insights and the thought processes. And as a number of us have suspected for a while, there's some interesting fruit that's still on the vine from many years ago. And so we'll see what we can do going forward. And I have it in my notes now, unapologetically bold, as my Adam K quote. So we'll definitely use that one and attribute that to you in the future. So I like that, unapologetically bold. Good stuff. If that's got some people thinking, please remember your questions for when we get to the final segment here. We have 2 more talks to go, and then we'll just go to some final Q&A. Thanks everybody for continuing to stick with us. We have next up Jerry Carson and Ray Sedgwick from University of Maryland. They will be talking about direct fusion drive based on centrifugal mirror confinement. So Jerry and Ray, you guys have the con, and I will put myself on mute.
All right, can you all see the screen?
Yes, we have it.
Okay, let me see if I can get into the slideshow here. So I'm going to keep my video off just because my router is at the other end of the house too. So if that's okay with y'all. This is a, can you see the outline chart right now? Is that showing up?
We've got it clear. It's good.
Okay. This is what's the points in the talk today. Just in the bottom right inset, there is a conceptual mission to Neptune, 4 years, an orbiter and 4 atmospheric probes. This is one possible instantiation of a 150 kilowatt jet power based on a fusion, direct fusion drive with centrifugal confinement. The advantage of a centrifugal confinement is it augments the mirror confinement, and so allows for a fairly compact form factor for pretty high power densities. And that's why we're interested in looking at it. So we'll go through a little background on centrifugal confinement and how it fits with a propulsion system, look at some of our current other research at Maryland that's going on that's complementary, and then the actual plan for work for the grant. So the goal for the overall effort is to get to a technology level readiness of 3, and that's basically because we expect to have and close the loop on a certain level of analytic studies, but we're also going to be working with our colleagues in the physics department as they work on the centrifugal mirror fusion experiment, which is using this centrifugal confinement, mirror confinement scheme to actually generate fusion. So there's an experimental level of achievement that we expect within the period of this grant that's going to be done in parallel by the folks at the Institute for Research in Electronics and Applied Physics, or IREAP. So that's what we're driving at. The team that are working on this and other parts, the Space Propulsion and Power Laboratory at Maryland. It's a multidiscipline organization. We have a sort of a hybrid of systems engineering combined with deep dives into specific technical problems. And we are highly cognizant of where other parts of the community are working. So in those cases, we may leave the heavy lifting in a certain domain to someone else, but we are interested in particular in things that are related to the propulsion system, superconducting magnets, shielding, things that get to what you would need in a practical system. So that's just a quick aside on what the SPPL team is bringing to the table. And now we'll just go ahead and dive into the actual idea of centrifugal mirror confinement. The central mechanism is an E cross B drift. That is when you combine an electric field, in this case, emanating from a central electrode in a radial direction with a generally longitudinal B field, you impose an azimuthal drift, which is very fast. We're talking, multiple Machs, and will confine the plasma to an annulus. It's in the cartoon there you see in the bottom. You can see the E and B fields working together, and the plasma cross section in the upper part of the annulus. And a simulation of that is off to the left, but I would want to point out that in the upper right is a photograph of the original Maryland confinement experiment, which demonstrated this method to confine plasmas up to 100 electron volts. So that work is being superseded by CMFX, which I'll talk about in just a minute. But the equation there is there because it shows once you get off of the midplane where you have a dot product with a magnetic field, those terms end up being non-zero. So we expect to a certain extent to get the radial confinement. But what that equation tells you is you also get an axial confinement, and that the solution to that equation is in the bottom left-hand corner. The burning plasma is that white blob toward the left of the screen as a half torus in cross section, and that's the volume of burning plasma that can be for a liter or a few liters and give you significant amounts of jet power to use for propulsion. So I'm going to move forward to the next chart. The propulsion system takes this concept, and because mirror devices are leaky, even with a centrifugal element to them, there will be high energy fusion products leaving the well axially, and they'll enter this warm plasma, which you'll see in the next graphic. It heats the warm plasma, and then the warm plasma then flows through a magnetic nozzle. That process does a couple of things. The first is that it steps down the temperature of the fusion products. It mitigates the tendency of the plasma to be frozen in. And frozen in is a condition that says a charged particle will tend to remain attached to the magnetic field unless there's some mechanism to allow it to break loose. In our case, collisional processes. Well, you may know that fusion plasmas are inherently collisionless for the most part, except for obviously where there is a collision which causes a fusion reaction. But in the scale that we need for propulsion, that is a problem. So the warm plasma serves to step down that temperature, and we're working in the 50 to 100 EV area, and then you can actually get the plasma to detach from the magnetic field and generate thrust. The energy leaving from the forward mirror is used to operate a standing wave direct energy conversion system. That's essentially like a particle accelerator in reverse. The plasma, the fusion products are modulated into groups, and they pass through a set of ring electrodes, and that standing wave is then turned into a power that can be turned around and used to drive the reactor. And we have we have generated solutions, families of solutions that show that you do have, from a first law standpoint, the energy to do that. So that's very interesting. Fusion propulsion system that couldn't power itself would not be particularly interesting. So, we're very concerned about having that ability. So I'm on chart 7 now. And, this is where this is a schematic of the system. You see the reactor, which we just saw in the schematic in that blue section. That's the electric field, and the green lines are the magnetic fields. And you get again those reactor wells. Leaving the reactor wells are the charged species, the alpha particles, and we're baselining a deuterium-tritium system for the first half of the grant. And when we looked at this in the first LSI cycle, which again you all support us on, Dr. White, we only looked at the charged particles. Now we're looking, at the alphas. Now we're looking at thermal species, which leave the well as well. And those thermal species, we believe, can add up to 10% of the jet power. The beta species are the propellant. That is the warm plasma. So you see in that one mixing region in the station 1, which is where all of these species combine, and then there's an energy exchange, and a particular amount of jet power is deposited into the plasma and then passes out through the magnetic nozzle. And then you see the charged particles going into the SWDC at forward end and generating the power that we use to generate the E field. We have several parallel efforts going on at the SPPL, and not just including the reactor dynamics. We're also looking at shielding, superconducting magnet operations, and power conversion. The graphic off to the right is a result of 4,000 solutions for our 0D model. The 0D model essentially means it's just considering constant properties within the plasma. And what it shows is the relationship between the Mach number, which is indicative of a centrifugal confinement, and the mirror ratio, which is indicative of the conventional mirror confinement. And you can sort of pick a point on that front where you want to operate. In general, we would like to operate more toward the higher Mach numbers, is so we can reduce the size of the mirror magnets. So our current effort in advance of this grant was to derive 2 or 3 point solutions from the from this 0D model, so that we could use those as models within the overall LSI task in deriving and simulating the warm plasma propulsion part. As I mentioned earlier, the IREP, the folks in the IREP part of UMD are building a follow-on to MCX with funding from ARPA-E. They have a goal of reaching a triple product of 10 to the 17, and with both hydrogen plasmas starting out and with deuterium plasmas, in which they hope to achieve fusion conditions. First plasma is planned for next year. This grant is built into 6 tasks. The first is to characterize the reactor propulsion system interface. We do have a fairly comprehensive view, even though it's not greatly in depth, a moderate fidelity model of the reactor. We know what power densities it can generate. We know what's required to power them. We know sort of the mix of prompt alphas, high energy 3.5 MeV products versus the thermal species. Before we looked at the thermal species, the major issue there was in the interface was the mirror ratio, because that really determined the percentage of the alpha particles that would leave the well. But now we're interested in the thermal species, and they actually have a bit to do to get out of the reactor well. There's a potential in that well that they have to overcome. So understanding, what energy they're going to lose leaving the well and what their arrival state will be in the warm plasma is that first task. The second one is building a 1D model of the warm plasma. Up to this point, it's been modeled in 0D, that is to say, assuming constant properties within the plasma. We're going to model in the radial direction, the heat equation, the momentum equation, and try to understand and model the variation in the velocity profiles of the plasma and its centrifugal motion, as well as the radial distribution of the transport properties. And these two items will then be rolled into a model for the magnetic nozzle and be able to do an end-to-end simulation of the system as a propulsion system. And that will be basically the first year of the grant that is looking at this end-to-end deuterium tritium system. In the second year, we're going to expand to more advanced fuels, deuterium and deuterium He3, and also try to scale some of the balance of plant, the superconducting magnets, as well as some of the key components of the power conversion. The CMFX team is generating a 1D reactor model. Its fidelity improves in the same way as our 1D warm plasma model improves over the 0D. And that will be integrated into the model during the second year as well, as to give us an even higher fidelity simulation. And then finally, we'll be doing a preliminary design or a conceptual design for warm plasma experiments. We want to get on a footing to start getting into the laboratory with the propulsion system. And the key focus for that will be verifying our understanding of the energy deposition rates and mechanisms. This is our schedule. I said, grouping it roughly into 2 years. The first year is getting that first end-to-end simulation, based on these newer, higher fidelity models over the original cycle. You do see the CMFX model that's not in this contract. We're going to be leveraging that. And we're about a year away from being able to need that drop. And in the second half, we'll be looking, more at a system level and expanding the power palette to a more exotic or more advanced fuels. So next steps, work in progress, is to baseline that DT reactor configuration and then start going into the grant itself and initially characterizing the reactor propulsion system interface with higher fidelity, and getting into the core of the task, which is that higher fidelity propulsion system modeling in the warm plasma. And I believe that's it.
Hey, thank you very much, Jerry, for the overview. Really appreciate that. That's good stuff to kind of look at what you guys are thinking about. And I think I'll also take the time to congratulate you and Ray for also having picked up a NASA grant on fusion propulsion. So I think I saw that on LinkedIn. I gave it my big thumbs up and said congrats to the University of Maryland team. So I know you've got some additional aspects of things you're looking at. So it's just nice to see your team get the recognition it deserves for all the good hard work that you've done to date. So
thank you. And again, thanks very much for this opportunity to work with y'all in LSI. We're looking forward to the work.
Awesome. Yes, sir. So we have one more presentation for today's LSI Grants Kickoff. We have Chathura Bandatunga from Australian National University. He will be giving us a presentation titled Navigating the Atmosphere, Transferring Terrestrial Beam Energy to Light Sail Spacecraft. And before you give your talk, I hope you've had some coffee, and thank you so very much for waking up very, very early to come join us, because I believe it's, 5 o'clock your time? a.m.?
It's not too bad. I'm actually coming from the Australian Institute of Physics Congress. So it's a big conference here in Australia. So the time zone shifted a bit in our favor.
Ah, okay. Well, we appreciate you. So
it looks like it's daylight outside.
It does look like it's daylight outside.
Or is that not?
Yeah, we're so far south. It rises at 5 a.m. So.
Oh, okay.
Oh, wow. All right, Chitra, I'm going to hand the con over to you for 20 minutes, and I'll give you a verbal at about 3 minutes till, just to let you know you're reaching the 20-minute window. So you have the con, sir.
Excellent. Thanks very much, and thank you for the introduction. It's great to be here. Can everyone see my slides just before I?
We see a black screen that says Chitra has started screen sharing, but I cannot see.
Oh. Zoom just crashed.
It says Teams.
I can still see you.
It says Teams or what?
No, it says Zoom.
Zoom.
Oh.
Yeah,
So you stop sharing.
Am I still here?
Yeah, we can see you and we can hear you. Can you see us and hear us?
Yes, it just crashed when I tried to share. Hang on, give me 1 second. Let's try that again. All right, share.
So worst case, I can present your charts and you can just tell me to go to the next slide. Hey, Chitra?
Yeah, it looks like it's not sharing. It just crashes when I start sharing. So
I have your charts. I will share your charts, and then you can just tell me to go to the next slide.
Yeah, much appreciated. Apologies for that.
Not a problem. Not a problem. So that easy to overcome this. The only request I have is if you present, like, sometimes people will have their PDF charts open in a separate window, and then they start going through the next slides, and they forget to tell me to go to the next slide, and then I got people online typing, I think he's on the next slide, go to the next slide. So
I'll let you know.
So I'm going to share my desktop here. Okay. I'm going to stop my video, make sure you can still hear me. All right. Bethera, can you see this?
Yeah, I can. And again, apologies for the technical difficulties. It is great to be. It is great to be here. I'm Chithura Bandatunga. I'm one of the team members on our current work at the Australian National University on optical phased arrays. And optical phased arrays has been a key part of our research portfolio for the last 6 or 7 years now. Gone through many PhD students and postgraduate students as well, postdoctoral students as well. It's currently hosted by the Center for Gravitational Astrophysics, and this is a unique center within the ANU, which is jointly administered by the Research School of Physics and the Research School of Astronomy and Astrophysics. And what that means for us is that we have our core academic staff, but we also have access to a lot of expertise from both of these fields and very easy access to them. So it gives us a really nice melting pot of technical expertise that we can bring to the field. So if we go to the next slide. The key thing that we're trying to achieve by doing this work is really to propel light sail spacecraft and to propel them from light sources which are located on Earth. And what this means is that we can use a fuel source essentially that does not need to be located on the spacecraft itself. And this is a concept that's not new at all. It's gone through a number of iterations. There's been a number of demonstrators as well, but the idea of using an actual ground-based laser as the light source to push on these sails is something that's yet to be fully realized. So the effect that we're trying to harness is really photon radiation pressure. This is just the transfer of momentum from light photons to a sail. Now, the acceleration that we achieve using this method is really proportional to the number of photons that's incident on the sail. And so the more photons we have, the faster we can go. But so the problem is that photon pressure is a very small effect. And so in order to get to any appreciable speed, we either need to integrate for a long time, we need to wait, or we just need a lot of photons. And that the second idea of needing a lot of photons is what a laser-driven light sail is trying to achieve. We go to the next slide. And so this brings us to the Breakthrough Starshot project. And this is something that we've been involved in at the ANU for the last few years. And I'm sure this has been brought up in the discussion so far, but just to quickly summarize, the Breakthrough Starshot project is an ambitious project to send a nano spacecraft or nanocraft to our nearest star system, Alpha Centauri, and to do so within a meaningful timeframe, a human timeframe. And to do that, we need to go at around 20% the speed of light. And that is aimed to be achieved using photon propulsion and a light sail. Once there, the sail will fly by Alpha Centauri, record science data, and transmit that back to Earth. You can already see that there's a whole host of challenges with this program. It's very ambitious, but the one we're focusing on is how do we accelerate? How do we get our sail from orbital speeds to relativistic speeds? And so we can ask the question, well, how many photons do we need? And given the initial proposed weight for this sail of 3.4 grams and a roughly 10-minute illumination window, that's the window over which the sail is within the field of view of the array on the Earth, we can calculate some numbers for laser power and the final sail speed after that illumination time. And you can see that the amount of power is quite large. We need on the order of 100 gigawatts to get to an appreciable fraction of the speed of light. The second question we ask is, okay, 100 gigawatts, let's roll with that number. How do we deliver that now from a ground-based system to our sail? And the concept drawing in the middle here, I really like, because it highlights the true scale of this project, even if this is clearly not the way to go. It was from the Breakthrough Starshot Communications Workshop, where we can see that if we were to use a single laser, imagining that it could reach 100 gigawatts, the optics for that would also be on a scale that's unfathomable at this point. So we need to work a little bit smarter. So what we're doing is we're trying to combine multiple lasers together. For 100 gigawatts, we require 100 million lasers, all working in concert. And the challenge then is getting 100 million lasers all working in concert to form a coherent beam in orbit that can also hit a light sail. And so this is the challenge. That challenge 2 is what we're really focusing on here. We go to the next slide. And so at ANU, as I've said, we've been working on phased arrays for a while. Our phased array technology allows us to measure the phase difference between each laser. This is an active measurement, so it's a continuous measurement, but continuously controlling each element of this optical phased array. And what's unique, or not unique, but what's nice about our architecture is that we do not require any optics beyond the emitter plane. So if you imagine the output optics of the optical phased array, all of our sensing is done internally to that. We don't need any beam splitters or external sampling of the beam. And this is novel on a small scale, like you can see on that's our optical head on the image in the top right. It's novel on a small scale, but it's absolutely necessary on the large scale required for something like Breakthrough Starshot. So keeping that in mind, we want to make internal measurements. We can then look at the atmosphere. So how do we, with this system, make internal measurements of the atmosphere that can then be used to correct, pre-distort the outgoing beams so that they coherently combine at the sail. This is quite difficult because the array itself is about a square mile in size, or 2.3 square kilometers. And so the area over which we need to perform this adaptive optics to correct for the atmosphere is very large. And if we look at conventional methods, for example, sodium laser guide star, Rayleigh laser guide stars, the altitude at which they illuminate is still very low. It's still within the Earth's atmosphere. And so the amount of atmosphere that's actually sampled by them over the size of the array is actually quite low. We need to do something a little bit different. And so with that, I'll jump over to talking a little bit about who we are on the next slide. So the team working on this, as I said, we're from the Applied Metrology Laboratories at the Center for Gravitational Astrophysics. We kind of take the ideas used for gravitational wave detection and apply them to other areas of high precision optical sensing. Myself, I'm currently leading the project. My background is in fiber sensing and a technique called digital interferometry. This is really combining RF pseudo-random modulation techniques with optical readouts for a hybrid digital optical methodology or approach to measurement. Dr. Paul Sibley is another pioneer of digital interferometry, and his background is actually on phased arrays. So he was developing and building the earlier prototypes, which I showed before. And we also have Michael Ireland, Professor Michael Ireland on the team. He has extensive experience in adaptive optics and stellar interferometry. So this is a bit of background about who we are and how we kind of banded together to try and come up with unique ideas for this problem. So if we go to the next slide. This was the concept that we came up with, and this is all published and supported by breakthrough initiatives for this initial phase of development. This is now published in an article in Joseph B, the Optica Journal. So do check that out. The key premise behind our control system for 100 million lasers is to basically do what we've already been doing. So we know that that architecture at its core works, and we just wanted to try and multiplex that. Can we combine can combine arrays with arrays? And that really is the crux of how we've gone about solving the problem. So we've broken the array down into sectors. You can see on the left, and then each sector is locked up as if we were locking up an optical phased array that we already do. Within each sector, we have modules, and those modules are within the sector locked up in the exact same way. And this continues on at the module level, which contains the individual kilowatt class lasers, which are the outgoing emission lasers. Between these different hierarchical levels, we use wavelength division multiplexing. And this allows us to isolate the control signals between each layer, but still manage to retain phase information and phase control of them. Within each layer, we use our technique, digital interferometry. This is a code division multiplexing technique, so it allows us to multiplex up to about 1,000 elements. And so as part of this initial work with Breakthrough Initiatives, we did extensive modeling of this control architecture just to validate its performance and make sure that it meets the necessary stability requirements for power transfer. But this still doesn't get to how we address the atmosphere. This is just the internal control system. So if we go to the next slide, this brings us to our atmospheric control system. And this is really the focus of our work that's supported generously by LSI. For our control system, if we go to the next slide, we have a beacon spacecraft. Now, this beacon spacecraft is within the field of view of the array during the illumination window. And there's a couple of unique things about this craft, and namely that it'll have a laser on board around 100 to 100 watts, and it will emit at 2 wavelengths. And these wavelengths will be frequency locked to an absolute frequency. So that absolute frequency will be known. The wavelength separation here is around 100 gigahertz. The reason for choosing 100 gigahertz is that we can use existing wavelength division multiplexing technology on the ground for the measurement. So that's the beacon spacecraft. It's now illuminating the array from within the isoplanetic angle of the laser sail during launch. That incoming wavefront, if we go to the next chart, is flat by the time it reaches the atmosphere. The orbital height of the beacon spacecraft is around 200,000 kilometers. So it's flat when it reaches the atmosphere. When it goes through the atmosphere, we get that distortion. If we go to the next chart. And as you can see, the distortion is going to be quite different between each aperture of the array. Each aperture is around 10 centimeters in size, which corresponds to a rough read parameter for a good launch site. It's the turbulence cell size for atmosphere. And so we can assume that the atmosphere across an individual emitter is roughly the same, but between emitters, it's definitely going to be different. The crux of what we do is this part 3, because as I've said, we've got 2 wavelengths coming down, and those wavelengths are separated from the emission wavelength. The reason for doing this is really, you've got 100 gigawatts going out. You need to be able to distinguish that clearly from the 100 watts distributed over 1 kilometer. So it turns into picowatts by the time it reaches our detector. So there's a huge dynamic range problem here, which we're solving by using multiple wavelengths, getting away from the emission wavelength. The challenge, though, is that what we need to correct is at the emission wavelength. So if we go to the next chart, because we're using a whole host of wavelengths, we need to make sure that we're correcting for the right phase. As we know, optical phase is the optical path length, which is the same for all of these paths, but it's divided by the wavelength, and the wavelength is different for all of these paths. And because of that difference, we need a way of taking those measurements, the measurements from the beacon spacecraft, and projecting it back to the emission wavelength. And this is really why we have 2 beacon wavelengths to begin with, because we can do a form of 2-color interferometry. If we go to the next chart, and so in doing that, we can calculate our correction at the emission wavelength for each emitter, and we can do this on a per emitter basis relative to one reference emitter. This can then be fed back to the lasers as a pre-correction, which will allow for, once the output field has propagated through the atmosphere, to reform into a flat wavefront. Now, the details and modeling of this, if we go to the next chart, we outlined in the paper that we published in JOSA B. So if you'd like further details on that, please do check that out. This is some of the simulation work that we did where we modeled for a 2-emitter system, because this is a differential measurement, a extraneous path length due to atmospheric turbulence, and then in the orange we have that path length now mapped to phase, modulo 1 cycle. In the blue we have the correction that we've now calculated from the beacon wavelengths to the emission wavelength, and taking the difference, we see that our residual is limited by quantum shot noise of the 2 beacon measurements. So we're fairly confident that this works. This was all done in numerical simulation. So what will our project with LSI allow us to do? So if we go to the next chart, what we're really excited for is really being able to test these algorithms out in the lab. And with LSI, we've got a seedling grant, which will allow us to make significant inroads in getting this experiment underway. And in particular, the crux of our problem is testing this projection algorithm. And in order to do that, we need it operating at high speed. This is something we have experience in, given our heritage in control systems, but actually implementing this in high-speed DSP will be the focus of this LSI seedling project. So to do that, we'll build a hardware in loop simulation. This will all be on National Instruments prototype hardware, FPGA systems, and we'll be building in the phase metrology, phase measurement DSP, as well as the wavelength projection DSP. So this, as you can see in this diagram here, we'll label the functional DSP, or functional signal processing. It will be the final, this is actually final digital signal processing for an experimental system. Surrounding it, we'll have simulation inputs and outputs, including simulated laser sources for beacons 1 and 2, and a simulated emission phase difference that we'll see. And so this hardware and loop simulation will allow us to rapidly stress test these functional signal processing blocks, and generate huge amounts of data in real time to really push this to the limit. And it's a key step towards implementing this in the lab. So following this work, would have strong confidence that our signal processing algorithms are working, and we can plug in optical signals in place of the simulated ones. Another small aspect of this project will look at cost reduction methods, especially regarding some of the modulator systems that will require for a really large phased array. So that will also be some of the work that's covered under this project. And with that, I'd like to summarize. So we've got at ANU, we've got a long history of working on optical phased arrays and other associated optical metrology systems. Over the past few years, we've had the opportunity to work with breakthrough initiatives on the Breakthrough Starshot mission, phase 1, coming up with a concept which we think is quite exciting to power light sail spacecraft to 20% of the speed of light. As part of that, we've developed a form of atmospheric correction for really large-scale optical phased arrays that we think will be able to efficiently transfer laser power from ground stations to light sails in orbit. This can, of course, be scaled down as well for shorter range missions or for remote power delivery. So the applications are quite wide. And this Limitless Space Institute seedling grant will really allow us to push ahead and start making inroads towards going onto physical hardware and testing this atmospheric correction algorithm in the lab. Thank you very much.
Thank you, Chathura. That was a very good overview. Hopefully it wasn't too hard to try and give your charts indirectly like that, right? So
it's perfect. Thank you.
Okay, so at this point, I think I would I'd like to open it up into just an open Q&A with the folks that are still with us. So I think I'd seen some hands raised a time or two. So Phil, I think you had a question during Charles Chase's presentation. So I remember you had one in the hopper. So if your powder's still dry, hit us with it.
Yeah, actually the two talks, once that Adam gave, as well as the one I was going to ask the question on, I mean, I think are really interesting areas to pursue. So one of the questions concerned the issue of the rotating element to kind of push on fluctuations. This idea that one can create photons out of oscillatory systems, which is I think not only a good idea, but it's the physics is very logical and I think well established. So the universe, however, is filled with a number of things. One of which is the photons that are from the early universe. So you have, in a sense, a state of things to which you can push against, in addition to, say, more exotic ways of thinking about it. So I wonder if you've thought about this issue. If you look at the number of photons that you're creating, I think it was 40,000 in the particular example that was given. And as you know, the universe is filled with about 400,000 photons per liter from the CMB, in addition to other sources. And particularly, say, in our solar system, it's even higher than that because of local sources from stars and dust emission. Anyway, just wanted to throw that out there and ask if you pondered that issue or not.
Yeah, thanks. That's a great question. Yeah, when we first started thinking about it, that was kind of our background. We were thinking about the background radiation, saying, okay, well, if we have like 3 Kelvin worth of black body radiation, where does that put us? And so one question we had related to that is actually kind of a dynamic drag force. Is this idea of quantum friction as well. And so if you start having a rotating object, presumably you'll have some friction associated with not just quantum friction, but also the actual traditional electromagnetic black body radiation that you have from the universe. So these are all kind of open questions that we hope to kind of consider with this program, but we haven't yet calculated that. So it'll be interesting to see where it goes.
Thank you, Jeremy. Phil, good question. What else we got?
I had a question for Jeremy. I was wondering, have you considered at all magnetoelectric materials or maybe even a full bianisotropic material and how that would behave?
Yeah, the short answer is no. It gets more complicated with all these more complicated materials. I think it's an excellent question because the idea is, basically any sort of electromagnetic boundary condition that you can have that you can change, you have the potential to generate dynamic photons. And so, yeah, I think these are all open questions that it'd be great to dive into that. It definitely gets more complicated with each kind of level that you extrapolate out to. But yeah, also very interesting direction, but we haven't tried that yet.
Yeah. Okay. Thank you.
Yeah, sorry, this is Sunny. I'm doing a quick zip over to the YouTube to see if I can catch any of the questions from over there as well. So I believe somebody else had their hand up, so go ahead and ask your question. Richard, did you have your hand up?
Yeah, I can also actually have a question for Chathura. So really nice, interesting talk. And I was wondering, you have kind of this other separate station where you can do some measurements that are in the periphery of your beam, but to kind of get a sense of what's being reflected and the effects from the atmosphere. Well, a question I always get with the light sails is always what happens to that reflected power, right? Like you're making a very good reflector, and you have all this power coming back. Is it coming back towards Earth? Kind of thing. And one question I kind of immediately think of is, can we use that reflected power in a way to diagnose what you're seeing in the atmosphere rather than having a separate station for it?
Yeah, really good question. And it's something that I think what's perhaps not apparent is how fast this will eventually be going. So by the end of that illumination window, it's a third of the way to Mars. So the transit time then becomes quite significant. And because the atmosphere is changing on the order of even hertz or the second, that transit time starts to really affect any control system that you might be trying to design. So this is why we need a beacon spacecraft that remains in orbit and actively illuminating, and instead of using the reflectance from the sail itself. Regarding the reflectance, though, coming back towards Earth, we can already see from the beacon that spreading that power over a square kilometer, we're getting nanowatts at each aperture, and then picowatts at our detector. So with that kind of power scaling, I think it's around 180 dB of loss total through the optical system. So it's also quite significantly attenuated.
Great. Thanks.
Thank you, Richard. Good question. What are the kind of questions that we got here? Yeah, go ahead, Adam.
Yeah, so I had a general question for Jeremy and or Charles about the 0-point field. I think Jeremy mentioned that the energy is technically infinite, and then there's ways of doing the cutoff, which, so far as I know, involves saying, oh, well, the highest energy photon that we have observed is this, and so we're only going to integrate up to that frequency. Even then, the energy density is absolutely enormous and something like 21 orders of magnitude different than what you would expect to see based on general relativity. And this is just the well-known cosmological constant problem, also called the vacuum catastrophe. I like that phrase because it kind of reminds one of the ultraviolet catastrophe and the questions in physics at the time that revolved around that. So I am just curious to know if you have any thoughts in general about that question that is circling around the 0-point field. And, it's an open question in physics, so I don't expect an answer. I'm just curious about your thoughts.
Charles, you want to go first? Yeah, I mean, so I don't have, I have nothing terribly illuminating to say about that. I mean, it's an open problem. I think in terms of the cutoffs, the way that I usually think about that, like from the Casimir force point of view, I think it's relatively straightforward because I can say, well, if I'm looking at metal plates, eventually they become transparent. And this is actually what Casimir was thinking about as well, I believe, from his original kind of derivations. So, once you start getting to, X-ray, then like your thin gold plates are not really, confining it very well. And so you've got a pretty reasonable cutoff. You can also start thinking about kind of Planck scale cutoffs where, like, once you start getting to those dimensions, maybe it doesn't really make sense to treat it the way that we currently are. So maybe that's another sort of cutoff. But you're right, when you look at any of those energy densities still, they're really high. So what can you make of that? And I don't know. It would be nice if they did match up, but they don't. So at least we have jobs for a while trying to figure out what's happening, right?
Yes, right.
Yeah, I don't have any great insights into that either. The 120 orders of magnitude comes when you use the Planck scale cutoff, which is, just really based on uncertainty principle. Right. I don't know. It's quite the conundrum. So, are vacuum fluctuations really real or not? Like I pointed out, you can come up with or determine the Casimir force without ever invoking vacuum fluctuations, just by assuming it's a radiation reaction force. You can also derive the Lamb shift in a similar way, but you don't have a consistent QED without the ground state energy. So the theory falls apart without that. So
that's right. And when I first became aware of this problem, it was talking to Carver Mead at Caltech, and his opinion was that QED is just a non-starter and it should fall apart exactly for the reason that you just said. Right. So, it's just a really interesting area.
Yeah. Have you followed Carver's collective electrodynamics approach to quantum theory then?
Yeah, I have that book. I haven't read the whole thing, but I like him a lot.
Yeah. He makes a pretty compelling argument in deriving quantum behavior from classical electromagnetics using a superconducting loop and the as sort of a model system. It's pretty interesting work. I know he tried to apply that to gravity as well, but I think the measurements of LIGO disproved his theory, so I haven't heard anything since that time.
No, I didn't know that, but that's very interesting.
Yeah.
That's the problem with QED, is it just works too well. Like
Right.
we keep making more and more measurements and they get more and more precise, but it always keeps matching.
But if you look at the standard model, there's at least 19 experimentally derived parameters that go into the model in order to, QCD, QED, to come up with the right values. Yeah, in my mind, that's not very fundamental when you have to find, that's kind of like fine tuning your theory. And yeah, it predicts new behavior, but it kind of tells me it's not really very fundamental.
Well, at the end of the day, right, an analog I use in discussion with folks, kind of talking about the things that LSI likes to think about, right, is, if you think about the two standard models of physics today, if you think about this as a Venn diagram, there's two circles on this Venn diagram, and in one circle you have the words quantum mechanics, and of course that represents our understanding of the microscopic world, and in the other circle you have the words general relativity, and that explains how the macroscopic world works. But those two theories, at best, those two circles only touch at a tangent point, in the context of the Dirac equation, if you will, right? And so, but beyond that, we know those two theories are not compatible to the point where they can overlap. And so we know we have some more generalized framework we have to chip out from the rock, if you will, as we try and dig out this dinosaur bone of better understanding, whatever that might be, right? And it's I think that the fact that these questions remain are just continued evidence that we're not done, right? And I don't know that we'll ever be done. Some people like to talk about, well, is this the theory of everything, and is this the theory of everything? And I'm like, I think there's probably going to be maybe 50 iterations over time as we just continue to improve our understanding of things. And right, I don't know that we'll ever reach a theory of everything, right? So
yeah, maybe it'll be the De Broglie Zitterbug. That'll be the thing.
Right. So, any last questions from the group? I think I got time for one more.
Maybe I could ask a quick one to Jeremy.
Yes.
So you were talking about these kind of rotating structures where you can rotate them fast enough to get a little bit of propulsion if there's just some kind of anisotropy in the optics. Have people already seen this with these kind of optically levitated kind of dumbbell structures, or they can also levitate them and rotate them to gigahertz? I would assume that kind of at a small scale is anisotropic and would somehow produce a small thing that might even kick it out of its trap or something like that. Is that something that's been observed?
It has not been observed. And so, I think those are the types of experiments I think that are promising for looking at this type of phenomenon. You probably want to try to redirect your geometry a little bit so that it's not rotating and emitting in all directions. I think in the dumbbell sorts of structures, you'd probably have equal photon probability of being kicked upward or downward, and that might kind of stabilize it as well. Granted, it's going to be a small kind of radiation pressure force anyway, but what you maybe want to do is have something where you've got a reflector at the top part. So if I'm thinking about even just a disc that's a birefringent crystal, if you were to put, say, metal on one side so it acts as a mirror, so you'd have kind of preferentially downward pointing emitted photons, that would kind of help, guide it. But yeah, I think those are the types of experiments to be thinking about.
Yeah. Do you know, Jeremy, if in those levitating dumbbell, did they ever look for photon emission like that?
Yeah, so I spoke with the Purdue group that was working on this, and I think that this is kind of in the back of their mind that they could be having some other Casimir or dynamic Casimir type effects, but I don't think that they've been looking for these kinds of things yet. Yeah. I think on the scale that they're working, I think it's probably too much in the noise at this point.
Okay, yeah. That's a
I
great
think
thought.
that with one of those early experiments, they were actually looking at trying to do a torque, Casimir torque type experiment as well. So.
Isn't this the team that got the dumbbell spinning up to gigahertz speed or something like that?
Right.
That's right. Yeah, that's actually one of the reasons that I picked gigahertz as kind of a trial, value, because we knew that experimentally that can be done. Yeah.
Precedence is always helpful, right? So
yeah.
Yeah. I don't know if you remember from the Quest program, but Sean Wee's work on the gyotropic nanoparticle from the thermal contrast, the non-reciprocal particle get up to a terahertz rotation speed was the predicted value.
Okay, good. That gives us some more hope. Yes.
Terahertz rotation speed, that'll definitely sling your teeth right out of your head.
That's for sure. Yeah.
That's awesome. Okay, well, I think that takes us to just a little bit over time. Just want to say in closing, thank you so much, all of you, for talking to us about some of the things you're planning on doing. It's a real treat for LSI to be able to sponsor and lean in with you guys on everything that you're doing. By the way, John Scott just joined us here in the office, another NASA power and propulsion walk.
And howdy to Ray.
Oh, howdy to Ray, right. But anyway, just, it's really nice that we can do that. I wish we could do more, right? As we continue to grow as an organization, and we will try and do that, continue to form partnerships. But I think the most important thing is you are helping us make progress towards our mission and our vision, our pinnacle objective, right? You're helping us make real measurable progress. We're trying to push at the boundaries of what we know, both in physics and engineering, right? And this definitely puts us in that basic research on a bad day and applied research on a good day. But I think this is potentially maybe one of the most important fields that needs support. I'd love for NASA as an agency to even get more involved specifically in this domain. I know they have NIAC, but I'd love to see NIAC maybe even get more focused on the advanced power and propulsion stuff, because at the end of the day, I think that the next chapter of spaceflight is all about getting through space. We live in an age where we're mastering the art of getting to space, as we can see with commercial space flight, but it's all about how do we get through space in terms of these large distances. I think Jerry Carson showed a chart where he was talking about delta V as a function of time, or maybe that was also Phil. I can't remember what somebody showed one. It was beamed energy propulsion. I think that was you, Phil, that talked about the delta V to get to Mars with the 1G acceleration is like 150 kilometers a second delta V, right? And so getting through space really quickly, right, that drives delta V to very large numbers. And so we need to have some new tools in our toolbox as mission planners, right? So I know the three of us have all, in our capacity of NASA, have been involved in many mission architectures, and we've been digging around in that mission planners toolbox looking for what we could find to conquer the delta V's. So thank you for everything you do. Thank you for being willing to think about it. And thank you for being unapologetically bold, as Kay said earlier in the meeting. So please continue to be unapologetically bold, but also be very, very credible and rigorous. So thank you all very much. We'll post this on the YouTube so folks can link to it. We'll add some chapters So you can always share the link with people you know, just so they can look at what, your particular section of the talk or whatever. Thank you again. We'll continue to work hard. So thank you.
Thanks, everybody.
Thanks very much, everyone.
Thanks,
Very exciting.
Yeah.
All right. Awesome. Awesome stuff.
Thanks.
See ya.
Thanks, Sonny.
Sure.